A Short Account of the History of Mathematics by W. Rouse Ball. History of Mathematics from Descartes to Huygens circa 1635 to 1675. Part 3. Huygens. Christian Huygens was born at The Hague on April 14, 1629, and died in the same town on June 8, 1695. He generally wrote his name as Huygens, Hugens, but I follow the usual custom in spelling it as Huygens. It is also sometimes written as Huyghens. His life was uneventful, and is a mere record of the dates of his various works. In 1651 he published an essay in which he shewed the fallacy in a system of quadratures proposed by Gregoire de Saint Vincent, who was well versed in the geometry of the Greeks, but had not grasped the essential points in the more modern methods. This essay was followed by tracts on the quadrature of the conics and the approximate rectification of the circle. In 1654 his attention was directed to the improvement of the telescope. In conjunction with his brother he devised a new and better way of grinding and polishing lenses. As a result of these improvements he was able during the following 2 years, 1655 and 1656, to resolve numerous astronomical questions, as for example the nature of Saturn's appendage. His astronomical observations required some exact means of measuring time, and he was thus led in 1656 to invent the pendulum clock, as described in his tract on Horologium, 1658. The timepieces previously in use had been balance clocks. In the year 1657 Huygens wrote a small work on the calculus of probabilities founded on the correspondence of Pascal and Fermat. He spent a couple of years in England about this time. His reputation was now so great that in 1665 Louis XIV offered him a pension if he would live in Paris, which accordingly then became his place of residence. In 1668 he sent to the Royal Society of London, in answer to a problem they had proposed, a memoir in which, simultaneously with Wallis and Wren, he proved by experiment that the momentum in a certain direction before the collision of two bodies is equal to the momentum in that direction after the collision. This was one of the points in mechanics on which Descartes had been mistaken. The most important of Huygens' work was in his Horologium Oscillatorium, published in Paris in 1673. The first chapter is devoted to the pendulum clocks. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. The second chapter contains a complete account of the descent of heavy bodies under their own weights in a vacuum, either vertically down or on smooth curves. Amongst other propositions he shews that the cycloid is tautochronous. In the third chapter he defines evolutes and involutes, proves some of their more elementary properties, and illustrates his methods by finding the evolutes of the cycloid and the parabola. These are the earliest instances in which the envelope of a moving line is determined. In the fourth chapter he solves the problem of the compound pendulum and shews that the centres of oscillation and suspension are interchangeable. In the fifth and last chapter he discusses again the theory of clocks, points out that if the bob of the pendulum were made by means of cycloidal checks to oscillate in a cycloid, the oscillations would be isochronous, and finishes by shewing that the centrifugal force on a body which moves in a circle of radius r with uniform velocity v varies directly as v squared and inversely as r. This work contains the first attempt to apply dynamics to bodies of finite size and not merely to particles. In 1675 Huygens proposed to regulate the motion of watches by use of the balance spring, in the theory of which he had been perhaps anticipated in a somewhat ambiguous and incomplete statement made by Hooke in 1658. Watches or portable clocks had been invented early in the 16th century and by the end of that century were not very uncommon, but they were clumsy and unreliable, being driven by a main spring and regulated by a conical pulley and verge escapement. Moreover, until 1687 they had only one hand. The first watch whose motion was regulated by a balanced spring was made at Paris under Huygens directions and presented by him to Louis XIV. The increasing intolerance of the Catholics led to his return to Holland in 1681, and after the revocation of the Edict of Nantes he refused to hold any further communication with France. He now devoted himself to the construction of lenses of enormous focal length. Of these, 3 of focal length 123 feet, 180 feet, and 210 feet were subsequently given by him to the Royal Society in London, in whose possession they still remain. It was about this time that he discovered the achromatic eyepiece for a telescope, which is known by his name. In 1689 he came from Holland to England in order to make the acquaintance of Newton, whose Principia had been published in 1687, the extraordinary merits of which Huygens had at once recognized. On his return in 1690 Huygens published his treatise on light, in which the undulatory theory was expounded and explained. Most of this had been written as early as 1678. The general idea of the theory had been suggested by Robert Hooke in 1664, but he had not investigated its consequences in any detail. This publication falls outside the years considered in this chapter, but here it may be briefly said that according to the wave or undulatory theory space is filled with an extremely rare ether, and light is caused by a series of waves or vibrations in this ether, which are set in motion by the pulsations of the luminous body. From this hypothesis Huygens deduced that the laws of reflection and refraction explain the phenomenon of double refraction, and gave a construction for the extraordinary ray in biaxial crystals, while he found by experiment the chief phenomenon of polarization. The immense reputation and unrivalled powers of Newton led to the disbelief in the theory which he rejected and to the general adoption of Newton's emission theory. But it should be noted that Huygens' explanation of some phenomena, such as the colours of thin plates, was inconsistent with the results of experiments, nor was it until Young and Wollaston at the beginning of this century revived the undulatory theory and modified some of its details, and Fresnel elaborated their views, that its acceptance could be fully justified. Besides these works, Huygens took part in most of the controversies and challenges which then played so large a part in the mathematical world, and wrote several minor tracts. In one of these he investigated the form and properties of the catenary. In another he stated in general terms the rule for finding maxima and minima of which Fermat had made use, and shewed that the subtangent of an algebraical curve fxy equals 0 was equal to y fy by fx, where fy is the derivative of fxy regarded as a function of y. In some posthumous works issued at Leyden in 1703 he further shewed how from the focal lengths of the component lenses the magnifying power of a telescope could be determined, and explained some of the phenomena connected with halos and parhelia. I should add that almost all of his demonstrations, like those of Newton, are rigidly geometrical, and he would seem to have made no use of the differential or fluxional calculus, though he admitted the validity of the methods used therein. Thus, even when first written, his works were expressed in an archaic language, and perhaps received less attention than their intrinsic merits deserved. I have now traced the development of mathematics for a period which we may take roughly as dating from 1635 to 1675 under the influence of Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens. The life of Newton partly overlaps this period. His works and influence are considered in the next chapter. I may dismiss the remaining mathematicians of this time whom I dare to mention with comparatively slight notice. The following is an alphabetical list of the more remarkable among them. The dates given to those are the birth and death of the mathematician to whose name they are appended. Bachet, 1581 to 1638. Barrow, 1630 to 1677. Brochner, 1620 to 1684. Collins, 1625 to 1683. Coursier, 1604 to 1692. Debonne, 1601 to 1652. De la Lubert, 1600 to 1664. Frenicle, 1605 to 1670. Gregory, 1638 to 1675. Hooke, 1635 to 1703. Hood, 1633 to 1704. Kinckhuysen, 1630 to 1679. Mercator, 1620 to 1687. Mersenne, 1588 to 1648. Midorge, 1585 to 1647. Pell, 1610 to 1685. Ritchie, 1619 to 1692. Roberval, 1602 to 1675. Roemer, 1644 to 1710. St. Vincent, 1584 to 1667. Sluys, 1622 to 1685. Torricelli, 1608 to 1647. Turnhausen, 1631 to 1708. Van Schooten died in 1661. And Wren, 1632 to 1723. In the following notes I have arranged the above mentioned mathematicians so that as far as possible their chief contributions shall come in chronological order. Bachet. Claude Gaspard Bachet de Mézirac was born in Bourg in 1581 and died in 1638. He wrote the Problème Plaisant, 1612, second and enlarged edition, 1624, which contains an interesting collection of arithmetical tricks and questions, many of which are quoted in chapter 1 of my Mathematical Recreations and Problems, also Les Éléments arithmétiques, which exists in manuscript, and a translation of arithmetic by Diophantus. Bachet was the earliest writer who discussed the solution of indeterminate equations by means of continued fractions. Midorge. Claude Midorge, born in Paris in 1585 and died in 1647, belonged to a distinguished family of the robe, and was himself a councillor at Châtelet, then treasurer to the local parliament at Amiens. He published some works on optics, of which one issued in 1631 is extant, and in 1641 a treatise on conic sections. He also left a manuscript containing solutions of over 1,000 geometrical problems, many of which are said to be ingenious. The enunciations were published by M. Charles Henry in 1882. Mersenne. Marin Mersenne, born in 1588 and died in Paris in 1648, was a Franciscan friar who made it his business to be acquainted and correspond with the French mathematicians of that date and many of their foreign contemporaries. In 1634 he published a translation of Galileo's Mechanics. In 1644 he issued his Cogitata Physico-Mathematica, by which he is best known, containing an account of some experiments in physics. He also wrote a synopsis of mathematics, which was printed in 1664. The preface to the Cogitata contains a statement, probably due to Fermat, that in order that 2p minus 1 may be prime, the only values of p not greater than 257 which are possible are 1, 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257, to which list Herr Seelhoff has shewn we must add the number 61. With this addition the statement has been verified for all except 23 values of p, namely 61, 71, 89, 101, 103, 107, 109, 127, 137, 139, 149, 157, 163, 167, 173, 181, 193, 197, 199, 227, 229, 241, and 257. Of these values, Mersenne asserted that p equals 67, p equals 127, and p equals 257 make 2 to the exponent p minus 1 a prime, and that the other values make 2p minus 1 a composite number. It is most likely that these results are particular cases of some general theorem on the subject which remains to be discovered. The number 2 to the power 61 minus 1 contains 19 digits, and is the highest number at present known to be prime. Its value in digits is 2305843009213693951. The theory of perfect numbers depends directly on that of Mersenne's numbers. It is probable that all perfect numbers are included in the formula 2 to the power of p minus 1, as opposed to -1 plus 2 to the p, where -1 plus 2 to the p is prime. Euclid proved that any number of this form is perfect. Euler shewed that the formula includes all even perfect numbers, and there is reason to believe, though a rigid demonstration is wanting, that an odd number cannot be perfect. If we assume that the last of these statements is true, then every perfect number is of the above form. Thus if p equals 2, 3, 5, 7, 13, 17, 19, 31, 61, then by Mersenne's rule the corresponding values of -1 plus 2 to the p are prime. They are 3, 7, 31, 127, 8191, 131,071, 524,287, 2,147,483,647, and finally 2,243,843,9,213,693,951. And the corresponding perfect numbers are 6, 28, 496, 8,128, 33,550,336, 8,589,869,056, 137,438,691,328. Next is 2,305,843,000,000, 8,139,952,128. And finally 2 undecillion, 658 decillion, 455 nonillion, 991 octillion, 569 septillion, 831 hexillion, 744 quintillion, 654 quadrillion, 692 trillion, 615 billion, 953,842,176. De Beaume. Florimond de Beaume was born in Blois in 1601 and died in 1652. Wrote explanatory notes on the obscure and difficult analytical geometry of Descartes. He also discussed the superior and inferior limits to the roots of an equation. This was not published till 1659. Roberval. Gilles Personnier de Roberval, born at Roberval in 1602 and died at Paris in 1675, described himself from the place of his birth as de Roberval, a seigneurial title to which he had no right. He discussed the nature of the tangents to the curves, solved some of the easier questions connected with the cycloid, generalized Archimedes' theorems on the spiral, and wrote on mechanics and the method of indivisibles, which he rendered more precise and logical. He was a professor in the University of Paris and in correspondence with nearly all of the leading mathematicians of his time. A complete edition of his works was included in the old Memoirs of the Academy of Sciences, published in 1693. Van Schooten. Franz van Schooten, to whom we owe an edition of Vieta's works, succeeded his father, who had taught mathematics to Huygens, Hood, and Sluys as a professor at Leyden in 1646. He brought out in 1659 a Latin translation of Descartes' Geometrie, and in 1657 a collection of mathematical exercises in which he recommended the use of coordinates in space of 3 dimensions. He died in 1661. Saint Vincent. Gregoire de Saint Vincent, a Jesuit, born at Bruges in 1584 and died at Ghent in 1667, discovered the expansion of the logarithm of 1 plus x in ascending powers of x. Although a circle squarer, he is worthy of mention for the numerous theorems of interest which he discovered in his search after the impossible, and Montucla ingeniously remarks that no one ever squared the circle with so much ability except for his principal object with so much success. He wrote 2 books on the subject, one published in 1647 and the other in 1668, which cover some 2,000 or 3,000 closely printed pages. The fallacy in the quadrature was pointed out by Huygens. In the former work he had used indivisibles. An earlier work entitled Theoremata Mathematica, published in 1624, contains a clear account of the method of exhaustions which is applied to several quadratures, notably that of the hyperbola. For further details of St. Vincent's life and works, see L.A.J. Quetelet, Histoire des sciences chez les Blages, Brussels, 1866. Torricelli. Evangelista Torricelli, born at Faenza in October 15, 1608, died at Florence in 1647, wrote on the quadrature of the cycloid and conics, the theory of the barometer, the value of gravity found by observing the motion of 2 weights connected by a string passing over a fixed pulley, the theory of projectiles, and the motion of fluids. His mathematical writings were published in 1644. Hood. Johann Hood, a burgomaster of Amsterdam, was born there in 1633 and died in the same town in 1704. He wrote 2 tracts in 1659. One was on the reduction of equations which have equal roots. In the other he stated what is equivalent to the proposition that if f of xy equals 0 be the algebraical equation of a curve, then its subtangent is negative y of the partial derivative of x with respect to y divided by the partial derivative of x with respect to x. But being ignorant of the notation of the calculus, his enunciation is involved. Frenicle. Bernard Frenicle de Bessy, born in Paris circa 1605 and died in 1670, wrote numerous papers on combinations and on the theory of numbers, and also on magic squares. It may be interesting to add that he challenged Huygens to solve the following system of equations in integers: x squared plus y squared equals z squared, x squared equals u squared plus v squared, and x minus y equals u minus v. A solution was given by M. Pepin in 1880. Frenicle's miscellaneous works, edited by De la Hare, was published in the Memoires de l'Académie, volume 5, 1691. De Lalubert. Antoine de Lalubert, a Jesuit born in Languedoc in 1600, died at Toulouse in 1664, is chiefly celebrated for an incorrect solution of Pascal's problems on the cycloid, which he gave in 1660, but he has a better claim to distinction in having been the first mathematician to study the properties of the helix. Kinckhuysen. Gerard Kinckhuysen, born in Holland in 1630 and died in 1679, wrote in 1660 a textbook on analytical conics, in 1661 an algebra, and in 1669 formed a collection of geometrical problems solved by analytical geometry. Corsier. Pierre Corsier, a Jesuit, born at Troyes in 1604 and died in Auxerre in 1692, wrote on the curves of intersection of a sphere with a cylinder or cone, also on spherical polygons. The latter work was published in 1663. Ricci. Michel-Ange Ricci, born in 1619, made a cardinal in 1681 and died in Rome in 1692, wrote in 1666 a treatise in which he solved by Greek geometry those problems on maxima and minima and on tangents to curves which had been considered by Descartes, Pascal, and Fermat. N. Mercator. Nicholas Mercator, sometimes known as Kaufmann, born in Holstein about 1620, but resided most of his life in England. He went to France in 1683, where he designed and constructed the fountains at Versailles, but when they were finished, Louis XIV refused to make him the payment agreed on unless he would turn Catholic. He died of vexation and poverty in Paris in 1687. He wrote a treatise on logarithms entitled Logarithmotechnia, published in 1668, and discovered the series log of 1 plus x equals x minus x squared over 2 plus x squared over 3 minus x to the power 4 over 4, and so on. He proved this by writing the equation of a hyperbola in the form of y equals 1 over 1 plus x, which would be equal to 1 minus x plus x squared minus x cubed plus, and so on, to which Wallace's formula, stated before, could be applied. The same series had been independently discovered by St. Vincent. Barrow. Isaac Barrow was born in London in 1630 and died at Cambridge in 1677. He went to school first at Charterhouse, where he was so troublesome that his father was heard to pray that if it pleased God to take any of his children, he could best spare Isaac, and subsequently to Felsted. He completed his education at Trinity College, Cambridge. After taking his degree in 1648, he was elected to a fellowship in 1649. He then resided for a few years in college, but in 1655 he was driven out by the persecution of the Independents. He spent the next 4 years in the east of Europe, and after many adventures returned to England in 1659. He was ordained the next year and appointed to the professorship of Greek at Cambridge. In 1662 he was made professor of geometry at Gresham College, and in 1663 was selected as the first occupier of the Lucasian chair at Cambridge. He resigned the latter to his pupil Newton in 1669, whose superior abilities he recognized and frankly acknowledged. For the remainder of his life he devoted himself to the study of divinity. He was appointed the master of Trinity College in 1672, and he held the post until his death. He is described as low in stature, lean and of a pale complexion, slovenly in dress, and an inveterate smoker. He was noted for his strength and courage, and once when travelling in the east he saved the ship by his own prowess from capture by pirates. A ready and caustic wit made him a favourite of Charles II, and induced the courtiers to respect even if they did not appreciate him. He wrote with a sustained and somewhat stately eloquence, and with his blameless life and scrupulous conscientiousness he was an impressive personage of the time. His earliest work was a complete edition of the Elements of Euclid, which he issued in 1655. He published an English translation in 1660, and in 1657 an edition of the Data. His lectures, delivered in 1664, 1665, and 1666, were published in 1683 under the title of Lectiones Mathematicae. These are mostly on the metaphysical basis for mathematical truths. His lectures for 1667 were published in the same year, and suggest the analysis by which Archimedes was led to his chief results. In 1669 he issued his Lectiones Opticae Geometricae. It is said in the preface that Newton revised and corrected these lectures, adding matter of his own, but it seems probable from Newton's remarks in the fluxional controversy that the additions were confined to the parts which dealt with optics. This, which is his most important work in mathematics, was republished with a few minor alterations in 1674. In 1675 he published an edition with numerous comments on the first four books of the Conics of Apollonius and of the extant works of Archimedes and Theodosius. In the optical lectures many problems connected with the reflection and refraction of light are treated with great ingenuity. The geometrical focus of a point seen by a reflection or refraction is defined, and it is explained that the image of an object is the locus of the geometrical foci of every point on it. Barrow also worked out a few of the easier properties of thin lenses, and considerably simplified the Cartesian explanation of the rainbow. The geometrical lectures contain some new ways of determining the areas of the tangents of curves. The most celebrated of these is the method given for the determination of tangents to curves, and this is sufficiently important to require a detailed notice because it illustrates the way in which Barrow, Hood, and Sluys were working on the lines suggested by Fermat towards the methods of the differential calculus. Fermat had observed that the tangent at point P on a curve was determined if one other point besides P on it were known. Hence, if the length of the subtangent MT could be found, thus determining the point T, then the line TP would be the required tangent. Now Barrow remarked that if the abscissa and ordinate at a point Q adjacent to P were drawn, he got a small triangle PQR, which he called the differential triangle because its sides PR and PQ were the differences of the abscissa and ordinates of P and Q, so that TM to MP equals QR to RP. To find QR to RP, he supposed that XY were the coordinates of P, and x minus e, y minus a, those of Q. Barrow actually used P for x and M for y, but I alter these to agree with the modern practice. Substituting the coordinates of Q in the equation of the curve and neglecting the squares and higher powers of e and a as compared with their first powers, he obtained the ratio e to a. The ratio a over e was subsequently, in accordance with a suggestion made by Sluys, termed the angular coefficient of the tangent at the point. Barrow applied this method to the curves 1. X squared multiplied by the quantity x squared plus y squared equals r squared y squared. 2. X cubed plus y cubed equals r cubed. And 3. X cubed plus y cubed equals rxy, called Lagalande. 4. Y equals the quantity r minus x multiplied by the tangent of pi x divided by 2r, the quadratrix. And 5. Y equals r times tan pi x over 2r. It will be sufficient here if I take as an illustration the simpler case of the parabola y squared equals px. Using the notation given above, we have for the point P y squared equals px, and for the point Q y minus a quantity squared equals p multiplied by the quantity x minus e. Subtracting, we get 2ay minus a squared equals pe. But if a be an infinitesimal quantity, a squared must be infinitely smaller and therefore may be neglected. Hence the ratio e to a equals the ratio 2y to p. Therefore Tm to y equals e to a equals 2y to p. That is, Tm equals 2y squared divided by p, which is equal to 2x. This is exactly the procedure of the differential calculus, except that we there have a rule by which we can get the ratio a over e or dy by dx directly without the labor of going through a calculation similar to the above for every separate case. Bruckner. William Viscount Bruckner, one of the founders of the Royal Society of London, born in 1620 and died on April 15, 1684, was among the most brilliant mathematicians of his time, and was in intimate relations with Wallis, Fermat, and other leading mathematicians. I mentioned on page 155 his curious reproduction of Brahmagupta's solution of a certain indeterminate equation. Bruckner proved that the area enclosed between the equilateral hyperbola xy equal 1 and the axis of x, and the ordinates x equals 1 and x equals 2 is equal either to 1 over 1 times 2 plus 1 over 3 times 4 plus 1 over 5 times 6 plus and so on, or to 1 minus 1 half plus 1/3 minus a quarter and so on. He also worked out similar expressions for different areas bounded by the hyperbola and straight lines. He wrote on the rectification of the parabola and of the cycloid. It is noticeable that he used infinite series to express quantities whose values he could not otherwise determine. In answer to a request of Wallis to attempt the quadrature of the circle, he shewed that the ratio of the area of the circle to the area of the circumscribed square, that is, the ratio of pi to 4, is equal to the ratio 1 over 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 and so on to 1. Continued fractions had been introduced by Cataldi in his treatise on finding the square roots of numbers published at Bologna in 1613, but he treated them as common fractions. Bruckner was the first writer who investigated or made any use of their properties. For further details see C. Hutton's Mathematical Dictionary. James Gregory. James Gregory, born at Drumoke near Aberdeen in 1638 and died in Edinburgh in October 1675, was successively professor at St Andrews and Edinburgh. In 1660 he publishes Optica Promota, in which the reflecting telescope known by his name is described. In 1667 he issued his Vera Circuli et Hyperbolae Quadratura, in which he showed the areas of the circle and hyperbola could be obtained in the form of infinite convergent series, and here, I believe for the first time, we find a distinction drawn between convergent and divergent series. This work contains a remarkable geometrical proposition to the effect that the ratio of the area of any arbitrary sector to that of the inscribed or circumscribed regular polygons is not expressible by a finite number of algebraical terms. Hence he inferred that the quadrature was impossible. This was accepted by Montucla, but it is not conclusive, for it is conceivable that some particular sector might be squared, and this particular sector might be the whole circle. This book contains also the earliest enunciations of the expansions in the series of sin x, cosine of x, inverse sine of x, and inverse cosine of x. It was reprinted in 1668 with an appendix, Geometria Pars, in which Gregory explained how the volumes of solids of revolution could be determined. In 1671, or perhaps earlier, he established the theorem that theta equals tan theta minus 1/3 tan cubed theta minus 1/5 tan to the fifth theta, and so on, the result being true only if theta lie between negative 1/4 pi and positive 1/4 pi. This is the theorem on which the work of most of the subsequent calculation of approximations to the numerical value of pi has been based. For further detail see C. Hutton's Mathematical Dictionary. Wren. Sir Christopher Wren was born in Noyle in 1632 and died in London in 1723. Wren's reputation as a mathematician has been overshadowed by his fame as an architect, but he was Savilian professor of astronomy at Oxford from 1661 to 1673 and for some time president of the Royal Society. Together with Wallis and Huygens he investigated the laws of collision of bodies. He also discovered the two systems of generating lines on the hyperboloid of one sheet, though it is probable that he confined his attention to the hyperboloid of revolution. Besides these, he communicated papers on the resistance of fluids and the motion of the pendulum. He was a friend of Newton, and like Huygens, Hooke, Halley, and others, had made attempts to shew that the force under which the planets move varies inversely as the square of the distance from the sun. Wallis, Bruckner, Wren, and Boyle, the last named being a chemist and physicist rather than a mathematician, were the leading philosophers who had founded the Royal Society of London. The society arose from the self-styled Indivisible College in London in 1645. Most of its members moved to Oxford during the Civil War, where Hooke, who was then an assistant in Boyle's laboratory, joined in their meetings. The society was formally constituted in London in 1660 and was incorporated on 15th of July 1662. Hooke. Robert Hooke, born at Freshwater on July 18, 1635 and died in London on March 3, 1703, was educated at Westminster and Christ Church, Oxford, and in 1665 he became professor of geometry at Gresham College, a post which he occupied till his death. He is still known by the law which he discovered, that the tension exerted by a stretched string is, within certain limits, proportional to the extension, or as it is better stated, that the stress is proportional to the strain. He invented and discussed the conical pendulum, and was the first to state explicitly that the motions of the heavenly bodies were merely dynamical problems. He was as jealous as he was vain and irritable, and accused both Newton and Huygens of unfairly appropriating his results. Like Huygens, Wren, and Halley, he made efforts to find the law of force under which the planets move about the sun, and he believed the law to be that of the inverse square of the distance. He, like Huygens, discovered that the small oscillations of a coiled spiral spring were practically isochronous, and was thus led to recommend, possibly in 1658, the use of the balance spring in watches. He had a watch of this kind made in London in 1675. It was finished just 3 months later than the one made under the directions of Huygens in Paris. Collins. John Collins, born near Oxford on March 5, 1625, and died in London on November 10, 1683, was a man of great natural ability, but of slight education. Being devoted to mathematics, he spent his spare time in correspondence with the leading mathematicians of the time, for whom he was always ready to do anything in his power, and he has been described not inaptly as the English Mersenne. To him we are indebted for much information on the details of the discoveries of the period. Pell. Another mathematician who devoted considerable part of his time to making known the discoveries of others and to correspondence with leading mathematicians was John Pell. Pell was born at Sussex on March 1, 1610, and died in London on December 10, 1685. He was educated at Trinity College, Cambridge. He occupied in succession the mathematical chairs at Amsterdam and Breda. He then entered the English diplomatic service, but finally settled in 1661 in London, where he spent the last 20 years of his life. His chief works were an edition, with considerable new matter, of the Algebra by Brenker and Ronius, London 1668, and a table of square numbers, London 1672. For further details see my history of mathematics at Cambridge. Sluys. René François Walter de Sluys, or Slusius, canon of Liege, born on July 7, 1622, and died on March 19, 1685, found for the subtangent of a curve fxy equals 0 an expression which is the equivalent to negative y multiplied by the partial derivative delta f by delta y divided by the partial derivative delta f by dx. He wrote numerous tracts and in particular discussed at some length spirals and points of inflection. Tschirnhausen. Ehrenfried Walter von Tschirnhausen was born at Kislingswald on April 10, 1631, and died at Dresden on October 11, 1708. In 1682 he worked out the theory of caustics by reflection, or as they were usually called catacaustics, and shewed that they were rectifiable. This was the second case in which the envelope of a moving line was determined. He constructed the burning mirrors of great power. The transformation by which he removes certain intermediate terms from a given algebraical equation is well known. Romer. Olaf Romer was born at Aranus in September 25, 1644, and died in Copenhagen on September 19, 1710, and was the first to measure the velocity of light. This was done in 1675 by means of the eclipses of Jupiter's satellites. He brought the transit and mural circle into common use, the altazimuth having been previously generally employed, and it was on his recommendation that astronomical observations of stars were subsequently made in general on the meridian. He was also the first to introduce micrometers and reading microscopes into an observatory. He also deduced from the properties of epicycloids the form of the teeth and the toothed wheels best fitted to secure a uniform motion. End of part 23. Chapter 16. The life and works of Newton. The mathematicians considered in the last chapter commenced the creation of those processes which distinguish modern mathematics. The extraordinary abilities of Newton enabled him within a few years to perfect the more elementary of these processes, and to distinctly advance every branch of mathematical science then studied, as well as to create some new subjects. Newton was the contemporary and friend of Wallis, Huygens, and others of those mentioned in the last chapter, but though most of his mathematical work was done in between the years 1665 and 1686, the bulk of it was not printed, at any rate in book form, till some years later. I propose to discuss the works of Newton somewhat more fully than those of other mathematicians, partly because of the intrinsic importance of his discoveries, and partly because this book is mainly intended for English readers, and the development of mathematics in Great Britain was for a century entirely in the hands of the Newtonian school. Isaac Newton was born in Lincolnshire, near Grantham, on December 25th, 1642, and died at Kensington, London, on March 20th, 1727. He was educated at Trinity College, Cambridge, and lived there from 1661 till 1696, during which time he produced the bulk of his work in mathematics. In 1696 he was appointed to a valuable government office, and moved to London, where he resided till his death. His father, who had died shortly before Newton was born, was a yeoman farmer, and it was intended that Newton should carry on the paternal farm. He was sent to school at Grantham, where his learning and mechanical proficiency excited some attention, and as one instance of his ingenuity I may mention that he constructed a clock worked by water, which kept very fair time. In 1656 he returned home to learn the business of a farmer under the guidance of an old family servant. Newton however spent most of his time studying problems, making experiments, or devising mechanical models. His mother, noticing this, sensibly resolved to find some more congenial occupation for him, and his uncle, having been himself educated at Trinity College, Cambridge, recommended that he should be sent there. In 1661 Newton accordingly entered as a subsidar at Trinity College, where for the first time he found himself among surroundings which were likely to develop his powers. He seems somewhat to have but little interest for the general society or for any pursuits save science and mathematics, and he complained to his friends that he found the other undergraduates disorderly. Luckily he kept a diary, and we can thus form a fair idea of the course of education of the most advanced students at an English university at that time. He had not read any mathematics before coming into residence, but was acquainted with Sanderson's logic, which was then frequently read as preliminary to mathematics. At the beginning of his first October term he happened to stroll down to Southridge Fair, and there picked up a book on astrology, but could not understand it on account of the geometry and trigonometry. He therefore bought a Euclid, and was surprised to find how obvious the prepositions seemed. He thereupon read Oughtred's Clavis and Descartes' Geometrie, and the latter of which he managed to master by himself, though at some difficulty. The interest he felt in the subject led him to take up mathematics rather than chemistry as serious study. His subsequent mathematical reading as an undergraduate was found on Kepler's Optics, the works of Vieta, Van Schooten's Miscellanies, and Descartes' Geometrie, and Wallace's Arithmetica Infinitorum. He also attended Barrow's lectures. At a later time, on reading Euclid more carefully, he formed a high opinion of it as an instrument of education, and he used to express his regret that he had not applied himself to geometry before proceeding to algebraic analysis. There is a manuscript of his dated May 28, 1665, written in the same year as that which he took his BA degree, which is the earliest documentary proof of his invention of fluxions. It was about the same time that he discovered the binomial theorem. On account of the plague the college was shut down in the summer of 1665, and for a large part of the next year and a half Newton lived at home. This period was crowded with brilliant discoveries. He thought out the fundamental principles of his theory of gravitation, namely that every particle of matter attracts every other particle, and he suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. He also worked out the fluxional calculus tolerably completely. Thus in a manuscript dated November 13, 1665, he used fluxions to find the tangent and the radius of curvature at any point on a curve, and in October 1666 he applied them to several problems in the theory of equations. Newton communicated these results to his friends and pupils from and after 1669, but they were not published in print till many years later. It was also while staying at home at this time that he devised some instruments for grinding lenses to particular forms other than spherical, and perhaps he decomposed solar light into different colours. Leaving out details and taking round numbers only, his reasoning at this time on the theory of gravitation seems to have been as follows. He suspected that the force which retained the moon in its orbit about the earth was the same as terrestrial gravity, and to verify this hypothesis he proceeded thus. He knew that if a stone were allowed to fall near the surface of the earth, the attraction of the earth, that is, the weight of the stone, caused it to move through 16 feet in 1 second. The moon's orbit relative to the earth is nearly a circle, and as a rough approximation, taking it to be so, he knew that the distance of the moon, and therefore the length of its path. He also knew the time the moon took to go once round it, namely a month. Hence he could easily find its velocity at any point such as m. He could therefore find the distance mt through which he would move in the next second if it were not pulled by the earth's attraction. At the end of that second it was however at m prime, and therefore the earth must have pulled it through the distance tm prime in 1 second, assuming the direction of the earth pull to be constant. Now he and several physicists of the time had conjectured from Kepler's third law that the attraction of the earth on a body would be found to decrease as the body was removed further away from the earth in a proportion inversely as the square of the distance from the centre of the earth. If this were the actual law, and gravity were the sole force which retained the moon in its orbit, then Tm prime should be to 16 feet in a proportion which inversely is the square of the distance of the moon from the centre of the earth to the square of the radius of the earth. In 1679, when he repeated the investigation, Tm prime was found to have the value which was required by the hypothesis, and the verification was complete, but in 1666 his estimate of the distance of the moon was inaccurate, and when he made the calculation he found that Tm prime was about 1/8 less than it ought to have been on his hypothesis. This discrepancy does not seem to have shaken his faith in the belief that gravity extended to the moon and varied inversely as the square of the distance, but from Whiston's notes of a conversation with Newton it would seem that Newton inferred that some other force, probably Descartes' vortices, acted on the moon as well as gravity. This statement is confirmed by Pemberton's account of the investigation. It seems moreover that Newton already believed firmly in the principle of universal gravitation, that is, every particle of matter attracts every other particle, and suspected that the attraction varied as the product of their masses and inversely as the square of the distance between them. But it is certain that he did not then know what the attraction of a spherical mass on any external point would be, and he did not think it likely that a particle would be attracted by the earth as if the latter were concentrated into a single particle at its centre. On his return to Cambridge in 1667, Newton was elected to a fellowship at his college, and permanently took up his residence there. In the early part of 1669, or perhaps in 1668, he revised Barrow's lectures for him. The end of lecture 14 is known to have been written by Newton, but how much of the rest is due to his suggestions cannot now be determined. As soon as this was finished he was asked by Barrow and Collins to edit and add notes to a translation of Kinghuizen's Algebra, which he consented to do, but on condition that his name should not appear in the matter. In 1670 he also began a systematic exposition of his analysis by infinite series, the object of which was to express the ordinate of a curve in an infinite algebraical series, every term of which could be integrated by Wallace's rule. His results on the subject have been communicated to Barrow, Collins, and others in 1669. This was never finished. The fragment was published in 1711, but the substance of it had been printed as an appendix to the Optics in 1704. These works were only the first of Newton's leisure, most of the time during these 2 years being given up to optical researches. In October 1669 Barrow resigned the Lucasian chair in favour of Newton. During his tenure of the professorship it was Newton's practice to lecture publicly once a week, from half an hour to an hour at a time in one term of each year, probably dictating his lectures as rapidly as they could be taken down, and in the week following the lecture to devote 4 hours to appointments which he gave to students who wished to come to his rooms to discuss the results of the previous lecture. He never repeated a course, which usually consisted of 9 or 10 lectures, and generally the lectures of one course began from the point at which the preceding course had ended. The manuscripts of his lectures for 17 out of the first 18 years of his tenure are extant. When first appointed, Newton chose optics for the subject of his lectures and researches, and before the end of 1669 he had worked out the details of his discovery on the decomposition of a ray of white light into rays of different colours by means of a prism. The complete explanation of the theory of the rainbow followed from this discovery. These discoveries form the subject matter of the lectures which he delivered as Lucasian professor in the years 1669, 1670, and 1671. The chief new results were embodied in a paper communicated to the Royal Society in February 1672 and subsequently published in the Philosophical Transactions. The manuscript of his original lectures was printed in 1729 under the title Lectiones Opticae. This work is divided into 2 books, the first of which contains 4 sections and the second 5. The first section of the first book deals with the decomposition of solar light by a prism in consequence of the unequal refrangibility of the rays that compose it, and a description of his experiments is added. The second section contains an account of the method which Newton invented for the determining of the coefficients of refraction of different bodies. This is done by making a ray pass through a prism of the material so that the deviation is a minimum, and he proves that if the angle of the prism be I and the deviation of the ray be delta, then the refractive index will be the sine of 1/2 I plus delta multiplied by the cosecant half I. The third section is on refractions at plane surfaces. Here he shews that if a ray pass through a prism with minimum deviation, the angle of incidence is equal to the angle of emergence. Most of this section is devoted to geometrical solutions of different problems. The fourth section contains a discussion of refractions at curved surfaces. The second book treats of the theory of colours of the rainbow. By a curious chapter of accidents, Newton failed to correct the chromatic aberration of 2 colours by means of a couple of prisms. He therefore abandoned the hope of making a refracting telescope which should be achromatic, and instead designed a reflecting telescope, probably on the model of a small one which he had made in 1668. The form he used is that still known by his name. The idea of it was naturally suggested by Gregory's telescope. In 1672 he invented a reflecting microscope, and some years later he invented the sextant, which was rediscovered by Hadley in 1731. His professorial lectures from 1673 to 1683 were on algebra and the theory of equations, and are described below. But much of his time during these years was occupied with other investigations, and I may remark that throughout his life Newton must have devoted at least as much attention to the chemistry and theology as to mathematics, though his conclusions are not of sufficient interest to require mention here. His theory of colours and his deductions from his optical experiments were attacked with considerable vehemence by Paradis of France Linus and Lucas at Liege, Hooke in England, and Huygens in Paris, but his opponents were finally refuted. The correspondence which this entailed on Newton occupied nearly all his leisure in the years 1672 to 1675 and proved extremely distasteful to him. Writing on December 9, 1675, he says, "I was so persecuted with discussions arising out of my theory of light that I blame my own imprudence for parting with so substantial a blessing as my quiet to run after a shadow." Again, after November 18, 1676, he observes, "I see I have made myself a slave to philosophy, but, if I get rid of Mr. Linus's business, I will resolutely bid adieu to it eternally, excepting what I do for my private satisfaction or leave to come out after me. For I see a man must either resolve to put out nothing new, or to become a slave to defend it." The unreasonable dislike to have his conclusions doubted, or to be involved in any correspondence about them, was a prominent trait in Newton's character. He next set himself to examine the problem as to how light was really produced, and by the end of 1675 he had worked out the corpuscular or emission theory, a theory to which he was perhaps led by his researches on the theories of attraction. Only three ways have been suggested in which light can be produced mechanically. Either the eye may be supposed to send out something which, so to speak, feels the object, as the Greeks believed, or the object perceived may send out something which hits or affects the eye, as assumed in the emission theory. Or there may be some medium between the eye and the object may cause some change in the form or nature of this intervening medium and thus affect the eye, as Hooke and Huygens supposed in the wave or undulatory theory. It will be enough here to say that on either of the two latter theories all the obvious phenomena of geometrical optics, such as reflection, refraction, etc., can be accounted for. Within the present century crucial experiments have been devised which give different results according as one or the other theory is adopted. All these experiments agree with the results of the undulatory theory and differ from the results of the Newtonian theory. The latter is therefore untenable, but whether the former represents the whole truth and nothing but the truth is still an open question. Until, however, the theory of interference suggested by Young was worked out by Fresnel, the hypothesis of Huygens failed to account for all the facts, and was open to more questions than that of Newton. It should be noted that Newton nowhere expresses an opinion that the corpuscular theory is true, but always treats it as a hypothesis from which, if true, certain results would follow. It would moreover seem that he believed that the wave theory to be intrinsically more probable, and it was only the difficulty of explaining diffraction on that theory that led him to reject it. His remarks on the other physical subjects shew a similar caution. Newton's corpuscular theory was expounded in memoirs communicated to the Royal Society in December 1675, which are substantially reproduced in his Optics, published in 1704. In the latter work he dealt in detail with his theory of fits of easy reflection and transmission, and the colours of thin plates, to which he added an explanation of the colours of thick plates, and observations on the inflection of light. Two letters written by Newton in the year 1676 are sufficiently interesting to justify an allusion to them. Leibnitz, who had been in London in 1673, communicated some results to the Royal Society which he had supposed to be new, but which it was pointed out to him had been previously proved by Mouton. This led to a correspondence with Oldenburg, the secretary of the Society. In 1674 Leibnitz wrote, saying that he possessed general analytical methods depending on the infinite series. Oldenburg in reply told him that Newton and Gregory had used such series in their work. In answer to a request for information, Newton wrote on June 13, 1676, giving a brief account of his method, but adding the expansions of a binomial, i.e. the binomial theorem, and of the arc sine of x, from the latter of which he deduced that of sine of x. This seems to be the earliest known instance of the reversion of a series. He also inserted an expression for the rectification of an elliptic arc in an infinite series. Leibniz wrote on August 27th asking for fuller details, and Newton, in a long but interesting reply dated October 24th, 1676, and sent through Oldenburg, gives an account of the way in which he had been led to some of his results. In this letter Newton begins by saying that altogether he had used three methods for expansion in a series. His first was arrived at from the study of the method of interpolation by which Wallis had found expressions for the area of a circle and hyperbola. Thus, by considering the series of expressions 1 minus x squared quantity to the power 0 over 2, 1 minus x squared quantity to the power 2 over 2, and 1 minus x squared quantity to the 4 over 2, and so on, he deduced by interpolations the law which connects the successive coefficients in the expansions of 1 minus x squared to the power of a half, 1 minus x squared to the power of 3 halves, and so on, and then by analogy obtained the expression for the general term in the expansion of a binomial, i.e. the binomial theorem. He says that he proceeded to test this by forming the square of the expansion 1 minus x squared to the power of a half, which reduced to 1 minus x squared. And he proceeded in a similar way with other expansions. He next tested the theorem in the case of 1 minus x squared quantity to the power of 1 half by extracting the square root of 1 minus x squared, more arithmetico. He also used the series to determine the areas of the circle and the hyperbola in infinite series, and found that the results were the same as those he had arrived at by other means. Having established this result, he then discarded the method of interpolation in series and employed his binomial theorem to express, when possible, the ordinate of a curve in an infinite series in ascending powers of the abscissa, and thus, by Wallis's method, he obtained expressions in an infinite series for the areas and arcs of curves in the manner described in the appendix to his Optics and his De analysi per equationes numero terminorum infinitorum. He states that he had employed his second method before the plague in 1665-66, and goes on to say that he was then obliged to leave Cambridge, and subsequently, i.e. presumably on his return to Cambridge, he ceased to pursue these ideas as he found that Nicholas Mercator had employed some of them in his Logarithmotechnica published in 1668, and he supposed that the remainder had been or would be found out before he himself was likely to publish his discoveries. Newton next explains that he had also a third method, of which, he says, he had about 1669 sent an account to Barrow and Collins, illustrated by applications to areas, rectification, cubature, and etc. This was the method of fluxions, but Newton gives no description of it here, though he adds some illustrations of its use. The first illustration is on the quadrature of the curve represented by the equation y equals ax to the power m multiplied by the quantity b plus cx to the power n quantity to the power p, which he says can be effected as a sum of quantity m plus 1 divided by n terms if quantity m plus 1 divided by m be a positive integer, and which he thinks cannot otherwise be affected except by an infinite series. He also gives a list of other forms which are immediately integrable, of which chief are x is raised to the power of m times n minus 1 multiplied by open bracket a plus bx to the power n plus cx to the power of 2n close bracket raised to the power of minus 1. Next, x to the power of open bracket m plus 1 half close bracket n minus 1 multiplied by open bracket a plus b x to the power of n plus c x to the power of 2n close bracket raised to the power of minus 1. The next term x to the power of m times n minus 1 multiplied by open bracket a plus b x to the power of n plus c x to the power of 2n close bracket raised to the power of plus or minus a half. Next term x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket plus or minus a half open bracket c plus dx to the power of n close bracket raised to the power of minus 1. Next term x to the power of m times n minus 1 multiplied by open bracket a plus bx to the power of n close bracket raised to the power of 1 half multiplied by open bracket c plus dx to the power of n close bracket raised to the power of negative 1 half, where m is a positive integer and n is any number whatever. Lastly, he points out that the area of any curve can be easily determined approximately by the method of interpolation described below, in discussing his Methodus Differentialis. At the end of his letter, Newton alludes to the solution of the inverse problem of tangents, a subject on which Leibniz had asked for information. He gives formulae for reversing any series, but says that besides these formulae he has two methods for solving such questions, which for the present he will not describe except by an anagram, which being read is as follows: Une methodis consistent in extractione fluentis quantitatis ex equationes simul evolvente fluxionem ejus. Alteratantum in assumptione seriae pro quantitate qualibet incognitia ex qua cetera commodi derivare possunt, et in collagione terminorum homologorum equationis resultantis, ad eruendos terminos assumptae seriae. He implies in this letter that he is worried by the questions he has asked and the controversies raised about every new matter which he produces, which shew his rashness in publishing Quod ombrum captando e tennis perdiderum, quietam rem prosus substantialem. Leibniz did not reply to this letter till June 21st, 1677. In his answer he explains his method of drawing tangents to curves, which he says proceeds not by fluxions of lines but by the differences of numbers, and he introduces his notation of dx and dy for the infinitesimal differences between the coordinates of two consecutive points on a curve. He also gives a solution of the problem to find a curve whose subtangent is constant, which shews that he could integrate. In 1679 Hooke, at the request of the Royal Society, wrote to Newton expressing a hope that he would make further communications to the Society and informing him of various facts then recently discovered. Newton replied saying that he had abandoned the study of philosophy, but he added that the earth's diurnal motion might be proved by the experiment of observing the deviation from the perpendicular of a stone dropped from a height to the ground, an experiment which was subsequently made by the Society and succeeded. Hooke in his letter mentioned Picard's geodetical researches. In these Picard used a value of the radius of the earth which is substantially correct. This led Newton to repeat with Picard's data his calculations of 1666 on the lunar orbit, and he found the verification of his view was complete. He then proceeded to the general theory of motion under a centripetal force, and demonstrated (1) the equitable description of areas, (2) that if an ellipse were described about a focus under a centripetal force, then the law was that of the inverse square of the distance, 3, and conversely that of the orbit of a particle projected under the influence of such a force was a conic, or it may be, he thought, only an ellipse. Obeying his rule to publish nothing which could land him in scientific controversy, these results were locked up in his notebooks, and it was only a specific question addressed to him 5 years later that led to their publication. The Universal Arithmetic, which is on algebra, theory of equations, and miscellaneous problems, contains the substance of Newton's lectures during the years 1673 to 1683. His manuscript of it is still extant. Whiston extracted somewhat reluctant permission from Newton to print it, and it was published in 1707. Amongst several new theorems on various points in algebra and the theory of equations, Newton here enunciated the following important results. He explained that the equations whose roots are the solution of a given problem will have as many roots as there are different possible cases, and he considered how it happened that the equation to which a problem led might contain roots which did not satisfy the original question. He extended Descartes' rule of signs to give limits to the number of imaginary roots. He used the principle of continuity to explain how two real and unequal roots might become imaginary in passing through equality, and illustrated this by geometrical considerations. Thence he shewed that imaginary roots must occur in pairs. Newton also here gave rules to find a superior limit to the positive roots of a numerical equation, and to determine the approximate values of the numerical roots. He further enunciated the theorem known by his name for finding the sum of the nth powers of the roots of an equation, and laid the foundation of the theory of symmetrical functions of the roots of an equation. The most interesting theorem contained in the work is his attempt to find a rule analogous to that of Descartes for real roots, by which the number of imaginary roots of an equation can be determined. He knew that the result which he obtained was not universally true, but he gave no proof and did not explain what were the exceptions to the rule. His theorem was as follows. Suppose the equation to be of the nth degree arranged in descending powers of x, the coefficient of x to the n being positive, and suppose the n plus 1 fractions 1, n over n plus 1 multiplied by 2 over 1, n minus 1 over n minus 2 multiplied by 3 over 2, and so on. And then the middle term of the series would be n minus p plus 1 all divided by n minus p, that fraction multiplied by p plus 1 over p, and so on, and the second last term being 2 over 1 multiplied by the fraction n over n minus 1, and finally the final term 1. To be formed and written below the corresponding terms of the equation, then, if the square of any term when multiplied by the corresponding fraction be greater than the product of the terms on each side of it, put a plus sign above it, otherwise put a minus sign above it, and put a plus sign above the first and last terms. Now consider any two consecutive terms in the original equation and the two symbols written above them. Then we may have any one of the four following cases. Alpha, the terms of the same sign and the symbols of the same sign. Beta, the terms of the same sign and the symbols of the opposite signs. Gamma, the terms of opposite signs and the symbols of the same sign. Delta, the terms of the opposite signs and the symbols of the opposite signs. Then it has been shewn that the number of negative roots will not exceed the number of cases alpha, and the number of positive roots will not exceed the number of cases gamma, and therefore the number of imaginary roots is not less than the number of cases beta and delta. In other words, the number of changes of signs in the row of symbols written above the equation is an inferior limit to the number of imaginary roots. Newton, however, asserted that you may also know how many roots are impossible by counting the changes of sign in the series of symbols formed as above. That is to say, he thought that in general the actual number of positive, negative, and imaginary roots could be got only by the rule, and not merely superior or inferior to the limits of these numbers. but though he knew that the rule was not universal, he could not find what were the exceptions to it. This theorem was subsequently discussed by Campbell, Maclaurin, Euler, and other writers. At last, in 1865, Sylvester succeeded in proving the general result. In August 1684 Halley came to Cambridge in order to consult Newton about the law of gravitation. Hooke, Huygens, Halley, and Wren had all conjectured that the force of the attraction of the sun or earth on an external particle varied inversely as the square of the distance. These writers seem to have independently shewn that if Kepler's conclusion were rigorously true, as to which they were not quite certain, the law of attraction must be that of the inverse square, but they could not deduce from the law of the orbits of the planets. Halley explained that their investigations were stopped by their inability to solve this problem, and asked Newton if he could find out what the orbit of a planet would be if the law of attraction were that of an inverse square. Newton immediately replied that it was an ellipse, and promised to send or write out afresh the demonstration of it which he had found in 1679. This was sent in November of 1684. End of section 24. Chapter 16, part 1. Chapter 16, The Life and Works of Newton, part 2. Instigated by Halley, Newton now returned to the problem of gravitation, and before the autumn of 1684 he had worked out the substance of propositions 1 through 19, 21, 30, 32 through 35 in the first book of the Principia. These, together with the notes on the laws of motion and various lemmas, were read for his lectures in the Michaelmas term 1684. In November Halley received Newton's promised communication, which probably consisted of the substance of propositions 1, 11, and either 17 or corollaries 1 of 13, and thereupon he again went to Cambridge, where he saw a curious treatise, De Motu, drawn up since August. Most likely this contained Newton's manuscript notes of the lectures above alluded to. These notes are now in the University Library and are headed De Motu Corporum. Halley begged that the results might be published, and finally secured a promise that they should be sent to the Royal Society. They were accordingly communicated to the Society not later than February 1685 in the paper De Motu, which contained the substance of the following propositions in the Principia, book 1. Propositions 1, 4, 6, 7, 10, 11, 15, 17, 32, and book 2, propositions 2, 3, and 4. It seems also to have been due to the influence and tact of Halley at this visit in November 1684 that Newton undertook to attack the whole problem of gravitation and practically pledged himself to publish his results. As yet Newton had not determined the attraction of a spherical body on an external point, nor had he calculated the details of the planetary motions, even if the members of the solar system could be regarded as points. The first problem was solved in 1685, probably either in January or February. No sooner, to quote from Dr. Galisher's address on the bicentenary of the publication of the Principia, had Newton proved the superb theorem, and we know from his own words that he had no expectation of so beautiful a result till it emerged from his mathematical investigation that all the mechanism of the universe at once lay spread before him. When he discovered the theorems that from the first 3 sections of book 1, when he gave them in his lectures of 1684, he was unaware that the sun and earth exerted their attractions as if they were but points. How different must these propositions have seemed to Newton's eyes when he realized that these results, which he had believed to be only approximately true when applied to the solar system, were really exact! Hitherto they had been only true in so far as he could regard the sun as a point compared to the distance of the planets, or the earth as a point compared to the distance of the moon, a distance amounting to only about 60 times the earth's radius, but now they were mathematically true, excepting only for the slight deviation from a perfectly spherical form of the sun, earth, and planets. We can imagine the effect of this sudden transition from approximation to exactitude in stimulating Newton's mind to still greater efforts. It was now in his power to apply the mathematical analysis with absolute precision to the actual problems of astronomy. Of the three fundamental principles applied in the Principia, we may say that the idea that every particle attracts every other particle in the universe was formed at least as early as 1666. The law of equable distribution of areas, its consequences, and the fact that if the law of attraction were that of the inverse square of the orbit of a particle about a centre of force would be a conic, were proved in 1679, and lastly, the discovery that a sphere, whose density at any point depends only on the distance from the centre, attracts an external point as if the whole mass were collected at its centre, were made in 1685. It was this last discovery that enabled him to apply the first two principles to the phenomenon of bodies of finite size. The draft of the first book of the Principia was finished before the summer of 1685, but the corrections and additions took some time, and the book was not presented to the Royal Society until April 28, 1686. This book is given up to the consideration of the motion of particles or bodies in free space, either in known orbits, or under the action of known forces, or under their mutual attraction. In it, Newton generalizes the law of attraction into a statement that every particle of matter in the universe attracts every other particle with a force which varies directly as the product of their masses and inversely as the square of the distance between them, and he thence deduces the law of attraction for spherical shells of constant density. The book is prefaced by an introduction on the science of dynamics. The second book of the Principia was completed by the summer of 1686. This book treats of motion in a resting medium, and of hydrostatics and hydrodynamics, with a special application to waves, tides, and acoustics. He concludes it by shewing that the Cartesian theory of vortices is inconsistent both with the known facts and with the laws of motion. The next 9 or 10 months were devoted to the third book. Probably for this he had originally no materials ready. In it the theorems obtained in the first book are applied to the chief phenomenon of the solar system, the masses and distances of the planets, and, wherever sufficient data existed, of their satellites are determined. In particular, the motion of the moon, the various inequalities therein, and the theory of the tides are worked out in detail. He also investigates the theory of comets, shews that they belong to the solar system, explains how from 3 observations the orbit can be determined, and illustrates his results by considering certain special comets. The third book, as we have it, is but little more than a sketch of what Newton had finally proposed to himself to accomplish. His original scheme is among the Portsmouth Papers, and his notes shew that he continued to work at it for some years after the publication of the first edition of the Principia. The most interesting of his memoranda are those in which by means of fluxions he has carried out his results beyond the point at which he was able to translate them into geometry. Footnote. I take this opportunity of saying that I hope shortly to publish a memoir on the history and compilation of the Principia. The following brief summary of the contents of the work will give the reader a general idea of its arrangement. The Principia is preceded by a preface in which Newton says that his object is to apply mathematics to the phenomena of nature. Among these phenomena, motion is one of the most important. Now, motion is the effect of force, and though he does not know what is the nature or origin of force, still many of its effects can be measured, and it is these that form the subject matter of the work. The work begins, therefore, naturally with an introduction on dynamics or the science of motion. This commences with the 8 definitions of the various terms such as mass, momentum, and so on. Newton then lays down 3 laws of motion which are incapable of exact proof, but are confirmed partly by direct experiments, partly by the agreement with observation of the deductions from them. From these he deduces 6 fundamental principles of mechanics, and adds an appendix on the motion of falling bodies, projectiles, oscillations, impact, and the mutual attractions of 2 bodies. The most important deduction is that of the parallelogram of velocities, accelerations, and forces. The first book of the Principia is on the motion of bodies in free space, and is divided into 14 sections. The first section consists of 11 preliminary lemmas treated by the method of prime and ultimate ratios, and not by that of indivisibles. The second section commences by shewing that if a body, such as a planet, revolve in an orbit subject to a force tending to a fixed point, such as the sun, the areas swept out by radii drawn from the body to the point are in one plane and are proportional to the times of describing them. And conversely, if the areas be proportional to the times, the force acting on the body must be directed to the point. Newton then shews how, if the orbit be known and the centre of force be given, the law of force can be determined, and he finds the law for various curves. In the third section he applies these propositions to a body which describes a conic section about a focus, and proves that the force must vary inversely as the square of the distance, and that Kepler's third law would necessarily be true of such a system. Conversely, he proves that if a body were projected in any way and subject to a central force which varied according to this law, then it must move in a conic section having the centre of force in a focus. He concludes proposition 17, corollaries 3 and 4, with a suggestion as to how the effects of distributing forces should be calculated. This was first done by the brilliant investigations of Laplace and Lagrange. And Laplace says that Lagrange's paper in the Berlin Memoirs for 1786, on which the modern treatment of the subject is founded, was suggested by these remarks of Newton. The fourth and fifth sections are devoted to the geometry of conic sections, especially to the construction of conics which satisfy 5 conditions. In section 4, one of the conditions is that the focus is given. This includes the problem of finding the path of a comet from 3 observations which Newton says he found the most difficult problem of any which he had to solve. Curiously enough, he gave a second solution of the problem in book 3, proposition 41, in which he recommended as more simple but which is inapplicable in practice. The sixth section is devoted to determining what at any given time is the velocity, and what is the position of a body which is describing a given conic about a centre of attraction in a focus, together with various converse problems. To effect this, Newton had to find the area of a sector of a conic. This is easily done for the parabola. He then endeavours to shew that the exact quadrature of any closed oval curve having no infinite branches, such as the ellipse, is impossible. The proof is not correct as it stands, since the result is not true for ovals of the form y to the power of 2m equals the quantity a to the power of 2n minus x to the power of 2n, all multiplied by 2 to the power of 2m times n to the power of 2m multiplied by x to the power of 2m times 2n minus 1, where m and n are positive integers. Newton seems himself to have felt some doubt about inserting it, though he believed the result to be true. An exact quadrature being impossible, he proceeds to give 3 ways, 2 arithmetical and 1 geometrical, of approximating to the sectorial area of an ellipse as closely as is desired. The seventh section is given up to the discussion of motion in a straight line under a force which varies inversely as the square of the distance, and its comparison with the motion in a conic under the same force. He concludes by giving a general solution for all the problems considered in this section for any law of force. He here determines geometrically what is equivalent to finding the integral of x divided by the square root of the quantity ax minus x squared. The eighth section contains a general solutions for any orbit described under any central force of some of the problems previously considered. In proposition 40 he states that the kinetic energy acquired by a body in moving from one point to another is equal to the total work done by the force between those 2 points. In the ninth section he discusses the case where the orbit is in motion in its own plane round the center of force and treats in detail of the motion of the apse line and the forces by which a given motion would be produced. Newton applied this reasoning, proposition 45 corollary 2, to the case of the moon. But the resulting motion of the apses only came out about 1/2 of the actual amount. The approximation was in fact not carried to a sufficiently high order. Newton was aware of the discrepancy, and as he explained the similar difficulty in the case of the nodes it had been long suspected. Goldfray's Lunar Theory, 2nd edition, article 68, that the scholium of the first edition to book 3 proposition 35 meant that he had found the explanation. Nowhere in the Principia does he however give any hint as to how this was effected, and that the true explanation of a difference which had long formed an obstacle to the universal acceptance of the Newtonian system was first given by Clairaut in 1752. The Portsmouth papers contain Newton's original work and shew that he had obtained the true value by carrying the approximation to a sufficiently high order. It also seems clear from these papers that Newton gave the corollary to book 1 proposition 45 as a mere illustration to the motion of the apses and orbits which are nearly circular and did not mean it to apply to the moon, but by an inadvertence in the 2nd and 3rd editions a reference to it as an authenticity for a result connected with the moon was added which would naturally deceive any reader. Newton left most of the revision to the 2nd edition to Cotes, and it is probable that the mistake is due to a blunder of the editor. Other questions connected with lunar and planetary irregularities are also discussed in this proposition, but the extreme conclusions of Newton misled all the early commentators, and even Laplace in his Système du Monde, published in 1796, speaks of Newton as having only roughly sketched out this part of the subject, leaving it to be completed when the calculus should be further perfected. But in the last volume of his Mécanique Céleste, published in 1825, he says that on more careful reading he has no hesitation in regarding it as among the most profound parts of the work. The 10th section is devoted to the consideration of motion of bodies along given surfaces, but not in planes passing through the center of force, with special reference to the vibration of pendulums and the determination of the accelerating effect of gravity. In connection with the latter problem, Newton investigates the chief geometrical properties of cycloids, epicycloids, and hypocycloids. In the 11th section are considered the problems connected with motions in orbits where the center of force is disturbed, or where the moving body is disturbed by other forces. Until calculus of variations was invented by Lagrange in 1755, it was impossible to do more than sketch out the principles on which the problem should be solved, and Laplace in his Mécanique Céleste was the first to work out most of the questions in any detail. Newton commences by considering the disturbance produced by the mutual action of two bodies revolving around one another. He then proceeds to consider the problem of 3 or more bodies which mutually attract one another. He first solves the question completely if the force of attraction varies directly as the distance. He next takes the case of the three bodies moving under their mutual attractions as in nature. This problem has not been yet solved generally, but in Newton's day it was beyond any analysis of which he had the command. He contrived however to work out roughly the chief effects of the disturbing action of the sun on the motion of the moon, proposition 66. This proposition was singled out by Lagrange as the most striking single illustration of the genius of Newton. To this proposition 22 corollaries are appended in which it is applied to determine the motion in longitude, in latitude, the annual equation, the motion of the apse line and of the nodes, the evection, the change in inclination of the plane of the lunar orbit, the precession of the equinoxes, and the theory of the tides. The greater part of the third book consists of the numerical application of these principles to the case of the moon and the earth. Lastly, Newton shewed how from the motion of the nodes of the interior constitution of the body could be roughly determined. Up to this point Newton had generally treated the bodies with which he dealt as if they were particles. He now proceeds in section 12 to consider the attraction of spherical masses which are either of uniform density or whose density at any point is a single valued function of the distance of the point from the centre of the sphere. These are worked out for any law of attraction. In section 13 he gives some general theorems on the theory of attractions and on some propositions dealing with the attractions of solids of revolution. But these problems are almost insoluble without the aid of the infinitesimal calculus, and the Newtonian account of them is incomplete. The 14th section contains a statement of some theories and experiments in physical optics, and a solution by geometry of some problems in geometrical optics, particularly on the form of aplanatic refracting surfaces of revolution. The second book of the Principia is concerned with hydromechanics, and especially with motion in a resisting medium. These questions are not worked out so completely as those treated in the first book, and though this book provided the basis on which much of the subsequent work of Daniel Bernoulli, Clairaut, D'Alembert, Euler, and Laplace were erected, it is not of the same epoch-making character as the first book. This book is divided into 9 sections. The motion of bodies in a medium where the resistance varies directly as the velocity is considered in the first section. The motions where resistance varies as the square of the velocity is discussed in the second section. The motion where the resistance can be expressed as a sum of two terms, one of which varies as the velocity and the other as the square of the velocity, is dealt with in the third section. The second section contains proposition 25, a construction for the shape of the solid of least resistance. No proof is given, and it had been long somewhat of a mystery to know how Newton had contrived to solve the problem without the use of calculus of variations. Newton's demonstrations, there are 2 of them, have been recently discovered in the Portsmouth collection. The fourth section is devoted to a spiral motion in a resisting medium. The fifth to the theory of hydrostatics and elastic fluids. The sixth to the motion of pendulums in a resisting medium. The seventh to hydrodynamics, especially to the motion of projectiles in air and other fluids. The eighth to the theory of waves, including the principles from which the chief effects of the wave hypotheses in light and sound are calculated, and in particular the velocity of sound is determined. In the 9th section Newton discusses the Cartesian theory of vortices. He begins by shewing that if there were no internal friction, the motion would be impossible. He must therefore assume some law of friction, and as a working hypothesis he supposes that the resistance arising from want of lubricity in the parts of a fluid is caeteris paribus, proportional to the velocity of which the parts of the fluid are separated from each other.
This hypothesis, as he himself remarks, is probably not altogether correct, but he thinks that it will give a general idea of the motion. He next proves that on this hypothesis that the motion would be unstable. He must therefore suppose that some constraining force prevents this catastrophe, and he then shews that in that case Kepler's third law could not be true. Lastly, he shews by independent reasoning that the hypothesis must lead to results which are inconsistent with Kepler's other two laws, and that both the vortices and the motion of the planets would necessarily be unstable.
Several continental mathematicians made attempts to modify the Cartesian hypothesis so as to avoid these conclusions, but they could never explain one phenomenon without introducing fresh difficulties. It may be taken that by 1750 the Cartesian theory was finally abandoned.
The third book is headed On the System of the World, and is concerned chiefly with the application of the results of the first book to the solar system. It is introduced by certain rules of philosophizing and as a list of certain data obtained from astronomical observations. The rules are: 1. We may only assume as the possible causes of phenomenon such causes as are sufficient to explain them and are also verae causae, a verae causa being one which is capable of detection and such that its connection with the phenomenon can be ultimately shewn by independent evidence. 2. Effects of a similar kind must have similar causes. 3. Whatever properties of bodies are found by experience to be invariable should be assumed to be so in places where direct experiments cannot be made. Newton commences by illustrating the universality of the law of gravitation and sketches out the principles which lead him to think that the solar system is necessarily stable. He determines that the mass of the moon, the masses of the planets, their distances from the sun, and their figures. In the first edition he estimated, proposition 37, that the ratio of the mass of the moon to that of the earth was approximately that of 1 to 26. In the second and third editions this was altered to a ratio which is nearly that of 1 in 40. But except for the mass of the moon, he approximates to the results now known with astonishing closeness. He finds the disturbing force exerted by the sun and the moon, and considers the 5 chief irregularities in the orbit of the moon. He next discusses the solar and lunar tides, determines the precession of the equinoxes, and finally shews how the elements of a comet can be determined by these observations, and applies his results to certain comets. Before this time it had been commonly believed that the comets had nothing to do with the solar system, though in 1681 Dorfel had shewn that the path of the great comet of 1680 was a parabola having the sun at its focus. Lastly, the Principia is concluded by a general scholium containing the reflection on the constitution of the universe and on the eternal, the infinite, and perfect being by whom it is governed. The chief alterations in the second edition, published in 1713, were the substitutions of simpler proofs for some of the propositions in the second edition of the first book, a more full and accurate investigation found on some fresh experiments made by Newton about the year 1690, and the resistance of fluids in the 7th section of the second book, and the addition of a detailed examination of the causes of the precession of the equinoxes and the theory of comets in the third book. The chief alterations in the third edition, published in 1726, were in the scholium on fluxions, and the addition of a new scholium on the motion of the moon's nodes, book 3, proposition 53. End of footnote. The demonstrations throughout the work are geometrical, but to readers of ordinary ability are rendered unnecessarily difficult by the absence of illustrations and explanations, and by the fact that no clue is given to the method by which Newton arrived at his results. The reason why it was presented in a geometrical form appears to have been that the infinitesimal calculus was then unknown,
and had Newton used it to determine the results which were in themselves opposed to the prevalent philosophy of the time, the controversy as to the truth of his results would have been hampered by a dispute concerning the validity of the methods used in proving them.
He therefore cast the whole reasoning into a geometrical shape, which, if somewhat longer, can at any rate be made intelligible to all mathematical students. So closely did he follow the lines of Greek geometry that he constantly used graphical methods, and represented forces, velocities, and other magnitude in the Euclidean way, by straight lines (Book 1, Lemma 10), and not by certain number of units. The latter and modern method had been introduced by Wallis and must have been familiar to Newton. The effect of his confining himself rigorously to classical geometry is that the Principia is written in a language which is archaic even if not unfamiliar.
The adoption of geometrical methods in the Principia for purposes of demonstration does not indicate a preference on Newton's part for geometry over analysis as an instrument of research, for it is known now that Newton used the fluxional calculus in the first instance in finding some of the theorems, especially those towards the end of book 1. And in book 2, and in fact one of the most important uses of that calculus is stated in book 2, lemma 2.
But it is only just to remark that at the time of its publication and for nearly a century afterwards the differential and fluxional calculus were not fully developed and did not possess the same superiority over the method he adopted by which they do now. And it is a matter of astonishment that when Newton did employ the calculus he was able to use it to so good an effect. The ability shewn in the translation in a few months of theorems so numerous and of so great complexity into the language of the geometry of Archimedes and Apollonius is, I suppose, unparalleled in the history of mathematics. The printing of the work was slow, and it was not finally published till the summer of 1687. The whole cost was borne by Halley, who also corrected the proofs and even put his own researches on one side to press the printing forward. The conciseness, absence of illustrations, and synthetical character of the book restricted the numbers of those who were able to appreciate its value, and though nearly all competent critics admitted the validity of the conclusions, some little time elapsed before it affected the current beliefs of educated men. I should be inclined to say, but on this point opinions differ widely, that within 10 years of its publication it was generally accepted in Britain as giving a correct account of the laws of the universe. It was similarly accepted within about 20 years on the continent, except in France, where the Cartesian hypothesis held its ground until Voltaire in 1738 took up the advocacy of the Newtonian theory. The manuscript of the Principia was finished by 1686. Newton devoted the remainder of that year to his paper on physical optics, the greater part of which is given up to the subject of diffraction. In 1687, James II, having tried to force the university to admit as a master of arts a Roman Catholic priest who refused to take oaths of supremacy and allegiance, Newton took a prominent part in resisting the illegal interference of the king, and was one of the deputation sent to London to protect the rights of the university. The active part taken by Newton in this affair led to his being in 1689 elected member for the university. This parliament only lasted 13 months, and on its dissolution he gave up his seat. He was subsequently returned in 1701, but he never took any prominent part in politics. On his coming back to Cambridge in 1690 he resumed his mathematical studies and correspondence. If he lectured at this time, which is doubtful, it was on the subject matter of the Principia. The two letters to Wallis, which he explained his methods of fluxions and fluents, which were written in 1692 and published in 1693. Towards the close of 1692 and throughout the 2 following years, Newton had a long illness, suffering from insomnia and general nervous irritability. Perhaps he never quite regained his elasticity of mind, and though after his recovery he shewed the same power in solving any question propounded to him, he ceased thenceforward to do original work of his own initiative, and it was somewhat difficult to stir him to activity in new subjects.
In 1694 Newton began to collect data connected with the irregularities of the moon s motion with the view of revising the part of the Principia which dealt with that subject.
To render the observations more accurate, he forwarded to Flamsteed a table of corrections for refraction which he had previously made. This was not published till 1721, when Halley communicated it to the Royal Society. The original calculations of Newton and the papers connected with it are in the Portsmouth collection, and shew that Newton attained it by finding the path of a ray by means of quadratures in a manner equivalent to the solution of a differential equation. As an illustration of Newton's genius, I may mention that even as late as 1754 Euler failed to solve the same problem. In 1782 Laplace gave a rule for constructing such a table, and his results agree substantially with those of Newton. I do not suppose that Newton would in any case have produced much more original work after his illness, but his appointment in 1696 as warden and his promotion in 1699 to the mastership of the Mint at a salary of £1,500 a year brought his scientific investigations to an end, though it was only after this that many of his previous investigations were published in the form of books. In 1696 he moved to London. In 1701 he resigned the Lacazian chair, and in 1703 he was elected president of the Royal Society. End of section 25.
Chapter 16. The Life and Works of Newton, Part 3. In 1704 Newton published his Optics, which contains the results of papers already mentioned. The first edition of this book were appended to two minor works which have no special connection with optics, one being on cubic curves, the other on the quadrature of curves and on fluxions. Both of them were old manuscripts with which his friends and pupils were familiar, but they were here published urbi et orbi for the first time. The first of these appendices is entitled Um Ratio Linearum Tertii Ordinis. The object seems to be to illustrate the use of analytical geometry, and as the application to conics was well known, Newton selected the theory of cubics. He begins with some general theorems, and classifies curves according as to whether their equations are algebraical or transcendental, the former being cut by a straight line in a number of points, real or imaginary, equal to the degree of the curve, the latter being cut by a straight line in an infinite number of points. Newton then shews that many of the most important properties of conics have their analogues in the theory of cubics, and he discusses the theory of asymptotes in curvilinear diameters. After these general theorems he commences his detailed examination of cubics by pointing out that a cubic must have at least one real point at infinity. If the asymptote or tangent at this point be a finite distance, it may be taken for the axis of y. This asymptote will cut the curve in 3 points altogether, of which at least 2 are at infinity. If the third point be a finite distance, then, by one of his general theorems on asymptotes, the equation can be written in the form of xy squared plus hy equals ax cubed plus bx squared plus cx plus d, where the axes of x and y are the asymptotes of the hyperbola, which is the locus of the middle points of all chords drawn parallel to the axis of y, while if on the third point in which this asymptote cuts the curve be also at infinity, the equation can be written in the form xy equals ax cubed plus bx squared plus cx plus d. Next, he takes the case where the tangent at the real point at infinity is not at a finite distance. A line parallel to the direction in which the curve goes to infinity may be taken as the axis of y. Any such line will cut the curve in 3 points altogether, of which one is by hypothesis at infinity and one is necessarily at a finite distance. He then shews that if the remaining point in which this line cuts the curve be at a finite distance, the equation can be written in the form y squared equals ax cubed plus bx squared plus cx plus d. While if it be at an infinite distance, the equation can be written in the form y equals ax cubed plus bx squared plus cx plus d. Any cubic is therefore reducible to one of the 4 characteristic forms. Each of these forms is then discussed in detail, and the possibility of the existence of double points, isolated ovals, etc. is worked out. The final result is that in all there are 78 possible forms which a cubic may take. Of these, Newton enumerated only 72. 4 of the remainder were mentioned by Stirling in 1717, and one by Nicole in 1731, and one by Nicholas Bernoulli at about the same time. In the course of the work Newton states the remarkable theorem that just as the shadow of a circle cast by a luminous point on a plane gives rise to all the conics, so the shadows of the curves represented by the equation y squared equals ax cubed plus bx squared plus cx plus d give rise to all the cubics. This remained an unsolved puzzle until 1731, when Nicole and Clairaut gave demonstrations of it. A better proof is that given by Murdoch in 1740, which depends on the classification of these curves into 5 species according as to whether their points of intersection with the axis of x are real and unequal, real and 2 of them equal, 2 cases, real and all equal, or finally 2 imaginary and 1 real. In this tract Newton also discusses double points in the plane and at infinity, and the description of curves satisfying given conditions, and the graphical solution of problems by the use of curves. The second appendix to the Optics is entitled De Quadratura Curvarum. Most of it had been communicated to Barrow in 1668 or 1669, and probably was familiar to Newton's pupils and friends from that time onwards. It consists of 2 parts. The bulk of the first part is a statement of Newton's method of effecting the quadrature and the rectification of curves by means of infinite series. It is noticeable as containing the earliest use in print of literal indices, and also the first printed statement of the binomial theorem. But these are introduced only incidentally. The main object is to give rules for developing a function of x in a series of ascending powers of x, so as to enable mathematicians to effect the quadrature of any curve in which the ordinate y can be expressed as an explicit algebraical function of the abscissa x. Wallis had shewn how this quadrature could be found when y was given as a sum of a number of multiples of powers of x, and Newton's rules of expansion here established rendered possible the similar quadrature of any curve whose ordinate can be expressed as a sum of an infinite number of such terms. In this way he effects the quadrature of the curves y equals a squared divided by the quantity b plus x, y equals the square root of a squared plus or minus x squared, or y equals the square root of x minus x squared, or y equals the square root of 1 minus ax squared divided by the square root of 1 minus bx squared. But the results are of course expressed as infinite series. He then proceeds to curves whose ordinate is given as an implicit function of the abscissa, and he gives a method by which y can be expressed as an infinite series in ascending powers of x, but the application of the rule to any curve demands in general such complicated numerical calculations as to render it of little value. He concludes this part by shewing that the rectification of a curve can be effected in a somewhat similar way. His process is equivalent to finding the integral with regard to x of the square root of 1 plus y squared in the form of an infinite series. I should add that Newton indicates the importance of determining whether the series are convergent, an observation far in advance of his time, but he knew of no general test for the purpose, and in fact it was not until Gauss and Cauchy took up the question that the necessity of such limitations were commonly recognized. The part of the appendix which I have just described is practically the same as Newton's manuscript De Analysi per Equationes Numero Terminorum Infinitas, which was subsequently printed in 1711. It is said that this was originally intended to form an appendix to Kinckhuysen's Algebra. The substance of it was communicated to Barrow and by him to Collins in letters of July 31st and August 12, 1669, and a summary of part of it was included in a letter of October 24, 1676, sent to Leibniz. It should be read in connection with Newton's Methodus Differentialis published in 1736. Some additional theorems are there given, and he discusses his method of interpolation, which had been briefly described in the letter of October 24, 1676. The principle is this: if y equals phi of x be a function of x, and if when x is successively put equal to a1, a2, and so on, the values of y be known, and be b1, b2, and so on, then a parabola whose equation is y equals p plus qx plus rx squared plus so on can be drawn through the points a1, b1, a2, b2, and so on, and the ordinate of this parabola may be taken as an approximation to the ordinate of the curve. The degree of the parabola will of course be one less than the number of the given points. Newton points out that in this way the areas of any curves can be approximately determined. The second part of this appendix to the optics contained in a description of Newton's method is fluxions. This is best considered in connection with Newton's manuscript on the same subject, which was published by John Coulson in 1736, and of which it is a summary. The fluxional calculus is one form of the infinitesimal calculus expressed in a certain notation, just as the differential calculus is another aspect of the same calculus expressed in a different notation. Newton assumed that all geometrical magnitudes must be conceived as generated by continuous motion. Thus a line may be considered as generated by the motion of a point, a surface by that of a line, a solid by that of a surface, a plane angle by the rotation of a line, and so on. The quantity thus generated was defined by him as the fluent or flowing quantity. The velocity of the moving magnitude was defined as the fluxion of the fluent. This seems to be the earliest definite recognition of the idea of a continuous function, though it had been foreshadowed in some of Napier's papers. The following is a summary of Newton's treatment of fluxions. There are two kinds of problems. The object of the first is to find the fluxion of a given quantity, or more generally, the relation of the fluents being given, to find the relation of their fluxions. This is equivalent to differentiation. The object of the second or inverse method of fluxions is from the fluxion or some relations involving it to determine the fluent, or more generally an equation being proposed exhibiting the relation of the fluxions of quantities to find the relations of those quantities or fluents to one another. This is equivalent either to integration, which Newton termed the method of quadrature, or to the solution of a differential equation which was called by Newton the inverse method of tangents.
The methods for solving these problems are discussed at considerable length. Newton then went on to apply these results to questions connected with the maxima and minima of quantities, the method of drawing tangents to curves, and the curvature of curves, namely, the determination of the centre of curvature, the radius of curvature, and the rate at which the radius of curvature increases. He next considered the quadrature of curves and the rectification of curves. In finding the maximum and minimum of functions of one variable, we regard the change of sign of the difference between two consecutive values of the function as the true criterion. But his argument is that when a quantity increasing has attained its maximum, it can have no further increment, or when decreasing it has attained its minimum and can have no further decrement. Consequently, the fluxion must be equal to nothing. It has been remarked that neither Newton nor Leibniz produced a calculus, that is, a classified collection of rules, and that the problems they discussed were treated from first principles. That no doubt is the usual sequence in the history of such discoveries, though the fact is frequently forgotten by subsequent writers. In this case I think the statement so far as Newton's treatment of the differential or fluxional part of the calculus is concerned is incorrect, as the foregoing account sufficiently shews. If a flowing quantity or fluent were represented by x, Newton denoted its fluxion by x dot, and the fluxions of x dot or second function of x by x dot dot, and so on. Similarly, the fluent of x was denoted by x written in a box, or sometimes by x prime, or x inside square brackets. The infinitely small part by which a fluent such as x increased in a small interval of time measured by omicron was called the moment of the fluent, and its value was shown to be x dot omicron. Newton adds the important remark that thus we may in any problem neglect the terms multiplied by the second and higher powers of omicron, and we can always find an equation between the coordinates of x, y of a point on a curve and their fluxions x dot, y dot. It is an application of this principle which constitutes one of the chief values of calculus. For if we desire to find the effect produced by several causes of a system, then if we can find the effect produced by each cause when acting alone in a very small time, the total effect produced in that time will be equal to the sum of the separate effects. I should here note the fact that Vince and other English writers in the 18th century used x dot to denote the increment of x and not the velocity with which it increased. That is, x dot in their writing stands for what Newton would have expressed by x dot omicron, and what Leibniz would have written as dx. I need not discuss in detail the manner in which Newton treated the problem above mentioned. I will only add that in spite of the form of his definition, the introduction into geometry of the idea of time was evaded by supposing that some quantity, e.g. the abscissa of a point on a curve, increased equably, and the required results then depend on the rate at which other quantities, e.g. the ordinate or the radius of curvature, increased relatively to the one so chosen. The fluent so chosen is what we now call the independent variable. Its fluxion was termed the principal fluxion, and of course if it were denoted by x, then x dot was constant and consequently x dot dot equaled 0. There is no question that Newton used the method of fluxions in 1666, and it is practically certain that accounts of it were communicated in manuscript to friends and pupils from and after 1669. The manuscript from which most of the above summary has been taken is believed to have been written between 1671 and 1677, and to have been in circulation at Cambridge from that time onward. It was unfortunate that it was not published at once.
Strangers at a distance naturally judged of the method by the letter to Wallis in 1692 or by the Tractatus de Quadratura Curvarum, and were not aware that it had been so completely developed at an earlier date. This was the cause of numerous misunderstandings. At the same time it must be added that all mathematical analysis was leading up to the idea and methods of the infinitesimal calculus. Foreshadowings of the principles and even of the language of that calculus can be found in the writings of Napier, Kepler, Cavalieri, Pascal, Fermat, Wallis, and Barrow. It was Newton's good luck to come at a time when everything was ripe for the discovery, and his ability enabled him to construct almost at once a complete calculus. The notation of the fluxional calculus is for most purposes less convenient than that of the differential calculus. The latter was invented by Leibniz in 1675 and published in 1684, some 9 years before the earliest printed account of Newton's method of fluxions. But the question whether the general idea of the calculus expressed in that notation was obtained by Leibniz from Newton, or whether it was invented independently, gave rise to a long and bitter controversy. The leading facts are given in the next chapter. The question is one of considerable difficulty, but I will here only say that from what I have read of the voluminous literature on the question, I think on the whole it points to the fact that Leibniz obtained the idea of the differential calculus from a manuscript of Newton's which he saw in 1675. I believe, however, that the prevalent opinion is that the inventions were independent. The remaining events of Newton's life require little or no comment. In 1705 he was knighted. From this time onward he devoted much of his leisure to theology and wrote at great length on the prophecies and predictions, subjects which had always been of interest to him. His Universal Arithmetic was published by Whiston in 1707, and his Analysis by Infinite Series in 1711, but Newton had nothing to do with the preparation of either of these for the press. His evidence before the House of Commons in 1714 on the determination of longitude at sea marks an important epoch in the history of navigation. The dispute with Leibniz as to whether he had derived the ideas of the differential calculus from Newton or invented it independently originated about 1708 and occupied much of Newton's time, especially between the years 1709 and 1716. In 1709 Newton was persuaded to allow Cotes to prepare the long talked of second edition of the Principia. It was issued in March of 1713. A third edition was published in 1726 under the direction of Henry Pemberton. In 1725 Newton's health began to fail. He died on March 20th, 1727, and 8 days later was buried with great state in Westminster Abbey. His chief works, taking them in their order of publication, are the Principia, published in 1687, the Optics, with appendices on cubic curves, the quadrature and rectification of curves by use of the infinite series, and the method of fluxions, published in 1704, and the Universal Arithmetic, published in 1707, the Analysis per series, fluxions, etc., published in 1711, Lectiones Opticae, published in 1729, Method of fluxions, etc., i.e. Newton's manuscript on fluxions, translated by J. Coulson and published in 1736, and the Methodes Differentiales, also published in 1736. In appearance Newton was short, and towards the close of his life rather stout, but well set, with a square lower jaw, brown eyes, and a very broad forehead, and a rather sharp features. His hair turned grey before he was 30, and remained thick and white and silver till his death. As to his manners, he dressed slovenly, was rather languid, and was often so absorbed in his own thoughts as to be anything but a lively companion.
Many anecdotes of his extreme absence of mind when engaged in any investigation have been preserved. Thus once when riding home from Grantham he dismounted to lead his horse up a steep hill. When he turned at the top to remount he found that he had the bridle in his hand while his horse had slipped it and gone away. Again, on the few occasions when he sacrificed his time to entertain his friends, if he left them to get more wine or for any similar reason, he would as often as not be found after the lapse of some time working out a problem, oblivious alike of his expectant guests and of his errand. He took no exercise, indulged in no amusements, and worked incessantly, often spending 18 or 19 hours out of the 24 in writing. In character he was religious and conscientious, with an exceptionally high standard of morality, having, as Bishop Brunet said, the whitest soul he ever knew. Newton was always perfectly straightforward and honest, but in his controversies with Leibnitz, Hooke, and others, though scrupulously just, he was not generous, and it would seem that he had frequently took offence at a chance of expression when none was intended. He modestly attributed his discoveries largely to the admirable work done by his predecessors, and once explained that if he had seen farther than other men it was only because he stood on the shoulders of giants. He summed up his own estimate of his work in the sentence, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." He was morbidly sensitive to being involved in any discussions. I believe that with the exception of his papers on optics, every one of his works was published only under pressure from his friends and against his own wishes. There are several instances of his communicating papers and results on condition that his name should not be published. Thus when in 1669 he had at Collier's request solved some problems on the harmonic series and on annuities which had previously baffled investigation, he only gave permission that his results should be published "so it be," as he says, "without my name to it, for I see not what there is desirable in public esteem. Were I able to acquire and maintain it, it would perhaps increase my acquaintance, the thing which I chiefly study to decline." In intellect he has never been surpassed and probably never been equalled. Of this his extant works are the only proper test. Perhaps the most wonderful single illustration of his powers was the composition in 7 months of the first book of the Principia. As specific illustrations of his ability I may mention his solutions of the problems of Pappus, of John Bernoulli's challenge, and of the question of orthogonal trajectories. The problem of Pappus is to find the locus of a point such that the rectangle under its distances from two different straight lines shall be in a given ratio to the rectangle under its distances from two other given straight lines. Many geometricians from the time of Apollonius had tried to find a geometrical solution and had failed, but what had proved insuperable to his predecessors seemed to have presented little difficulty to Newton, who gave an elegant demonstration as that the locus was a conic. Geometry, said Lagrange, was, when recommending the study of analysis to his pupils, is a strong bow, but it is one which only a Newton could fully utilize. As another example I may mention that in 1696 John Bernoulli challenged mathematicians (1) to determine the Brachistochrone, and (2) to find a curve such that if any line drawn from a fixed point O cut it in P and Q, then OP to the power n plus OQ to the power n would be a constant. Leibnitz solved the first of these questions after an interval of rather more than 6 months, and then suggested that they should be sent as a challenge to Newton and others. Newton received the problems on January 29, 1697, and the next day gave the complete solutions of both, at the same time generalizing the second question. An almost exactly similar case occurred in 1716 when Newton was asked to find the orthogonal trajectory of a family of curves. In 5 hours Newton solved the problem in the form in which it was propounded to him, and laid down the principles for finding trajectories. It is almost impossible to describe the effect of Newton's writings without being suspected of exaggeration. But if the state of mathematical knowledge in 1669 or at the death of Pascal or Fermat be compared with what was known in 1687, it will be seen how immense was the advance. In fact, we may say that it took mathematicians half a century or more before they were able to assimilate the work which Newton produced in those 20 years. In pure geometry, Newton did not establish any new methods, but no modern writer has shewn the same power in using those of classical geometry. In algebra and the theory of equations he introduced the system of literal indices, established the binomial theorem, created no inconsiderable part of the theory of equations. One rule which he enunciated in this subject remained, till a few years ago, an unsolved riddle which had overtaxed the resources of succeeding mathematicians. In analytical geometry he introduced the modern classification of curves into the algebraical and transcendental, and established many of the fundamental properties of asymptotes, multiple points, and isolated loops, illustrated by a discussion of cubic curves. The fluxional or infinitesimal calculus was invented by Newton in or before the year 1666, and circulated in manuscripts amongst his friends in and after the year 1669, though no account of the method was printed till 1693. The fact that the results are nowadays expressed in a different notation has led to Newton's investigations on this subject being somewhat overlooked. Newton further was the first to place dynamics on a satisfactory basis, and from dynamics he deduced the theory of statics. This was in the introduction to the Principia published in 1687. The theory of attractions, the application of the principles of mechanics to the solar system, the creation of physical astronomy, and the establishment of the law of universal gravitation are wholly due to him, and were first published in the same work. The particular questions connected with the motion of the earth and the moon were worked out as fully as was then possible. The theory of hydrodynamics was created in the second book of the Principia, and he added considerably to the theory of hydrostatics, which may be said to have been first discussed by Pascal. The theory of the propagation of waves, and in particular the application to determine the velocity of sound, is due to Newton and was published in 1687. In geometrical optics he explained amongst other things the decomposition of light and the theory of the rainbow. He invented the reflecting telescope, known by his name, and the sextant. In physical optics he suggested and elaborated the emission theory of light. The above list does not exhaust the subjects he investigated, but it will serve to illustrate how marked was his influence on the history of mathematics. On his writings and on their effects it will be enough to quote the remarks of 2 or 3 of those who were subsequently concerned with the subject matter of the Principia. Lagrange described the Principia as the greatest production of the human mind, and said that he felt dazed that such an illustration of what a man's intellect might be capable. In describing the effect of his own writings and those of Laplace, it was a favourite remark of his that Newton was not only the greatest genius that had ever existed, but he was also the most fortunate. For as there is but one universe, it can happen but to one man in the world's history to be the interpreter of its laws. Laplace, who is in general very sparing of his praise, makes of Newton the one exception, and the words in which he enumerates the causes which will always assure the the Principias a preeminence above all other productions of the human intellect, have often been quoted. Not less remarkable is the homage rendered by Gauss. For other great mathematicians or philosophers he used the epithets magnus or clarus or clarissimus. For Newton alone he kept the prefix summus. Finally, Biot, who had made a special study of Newton's works, sums up his remarks by saying: Comme géométrie et comme expérimentateur, Newton est sans égal. Par la réunion de ces deux genres de génie et leur plus haut degré, elle est sans exemple. End of section 26. Chapter 17. Leibniz and the mathematicians of the first half of the 18th century. Part 1. I have briefly traced in the last chapter the nature and extent of Newton's contributions to science. Modern analysis is however derived directly from the works of Leibniz and the elder Bernoullis, and it is immaterial to us whether the fundamental ideas of it were obtained by them from Newton or discovered independently. The English mathematicians of the years considered in this chapter continued to use the language and notation of Newton. They are thus somewhat distinct from their continental contemporaries, and I have therefore grouped them together in a section by themselves. Leibniz and the Bernoullis. Leibniz. Gottfried Wilhelm Leibniz was born at Leipzig on June 21st, 1646, and died at Hanover on November 14th, 1716. His father died before he was 6, and the teaching at the school to which he was then sent was inefficient, but his industry triumphed over all difficulties. By the time he was 12 he had taught himself to read Latin easily, and had begun Greek, and before he was 20 he had mastered the ordinary textbooks on mathematics, philosophy, theology, and law. Refused the degree of Doctor of Laws at Leipzig by those who were jealous of his youth and learning, he moved to Nuremberg. An essay which he there wrote on the study of law was dedicated to the Elector of Mainz, and led to his appointment by the Elector on a commission for the revision of some statutes, from which he was subsequently promoted to the diplomatic service. In the latter capacity he supported unsuccessfully the claims of the German candidate for the crown of Poland. The violent seizure of various small places in Alsace in 1670 excited universal alarm in Germany as to the designs of Louis XIV, and Leibniz drew up a scheme by which it was proposed to offer German cooperation if France liked to take Egypt and use the possession of that country as a basis for attack against Holland in Asia, on the condition that Germany was to be left undisturbed by France. This bears a curious resemblance to the similar plan by which Napoleon I proposed to attack England. In 1672 Leibniz went to Paris on the invitation of the French government to explain the details of the scheme, but nothing came of it. At Paris he met Huygens, who was then residing there, and their conversation led him to study geometry, which he described as opening a new world to him, though he had as a matter of fact previously written some tracts on various minor points in mathematics, the most important of them being a paper on combinations written in 1668, and a description of a new calculating machine. In January 1673 he was sent on a political mission to London, where he stopped some months and made the acquaintance of Oldenburg, Collins, and others. It was at this time that he communicated the memoir to the Royal Society, in which he was found to have been forestalled by Mouton. In 1673 the Elector of Mainz died, and in the following year Leibniz entered the service of the Brunswick family. In 1676 he again visited London, and then moved to Hanover, where till his death he occupied the well paid post of librarian in the Ducal Library.
His pen was thenceforth employed in all the political matters which affected the Hanoverian family, and his services were recognized by honours and distinctions of various kinds. His memoranda on the various political, historical, and theological questions which concerned the dynasty during the 40 years from 1673 to 1713 form a valuable contribution to the history of that time. His appointment in the Hanoverian service gave him an increased leisure for his favourite pursuits. Leibniz used to assert that as the first fruit of his increased leisure he invented the differential and integral calculus in 1674, but the earliest traces of the use of it in his extant notebooks do not occur till 1675, and it was not till 1677 that we find it developed into a consistent system. It was not published until 1684. Nearly all his mathematical papers were produced within the 10 years, from 1682 to 1692, most of them in a journal called the Acta Eruditorum, which he and Otto Mencke founded in 1682, and which had a wide circulation on the continent. Leibniz occupies at least as large a place in the history of philosophy as he does in the history of mathematics. Most of his philosophical writings were composed in the last 20 or 25 years of his life, and the point as to whether his views were original or whether they were appropriated from Spinoza, whom he visited in 1676, is still in question among philosophers, though the evidence seems to point to the originality of Leibniz. As to Leibniz's system of philosophy, it will be enough to say that he regarded the ultimate elements of the universe as individual percipient beings whom he called monads. According to him the monads are centres of force, and substance is force, while space, matter, and motion are merely phenomenal. Finally, the existence of God is inferred from the existing harmony among the monads. His services to literature were almost as considerable as those to philosophy. In particular, I may single out his overthrow of the then prevalent belief that Hebrew was the primeval language of the entire human race. In 1700 the Academy of Berlin was created on his advice, and he drew up the first body of statutes for it. On the accession in 1714 of his master George I to the throne of England, Leibniz was practically thrown aside as a useless tool. He was forbidden to come to England, and the last 2 years of his life were spent in neglect and dishonour. He died at Hanover in 1716. He was over fond of money and personal distinctions, was unscrupulous, as might be expected of a professional diplomat of that time, but possessed singularly attractive manners, and all who once came under the charm of his personal presence remained sincerely attached to him. His mathematical reputation was largely augmented by the eminent position that he occupied in diplomacy, philosophy, and literature, and the power thence derived was considerably increased by his influence in the management of the Acta Eruditorum, which I believe was the only private scientific journal of the time. The last years of his life, from 1709 to 1716, were embittered by the long controversy with John Keill, Newton, and others as to whether he had discovered the differential calculus independently of Newton's previous investigations, or whether he had derived the fundamental idea from Newton and merely invented another notation for it. The controversy occupies a place in the scientific history of the early years of the 18th century quite disproportionate to its true importance, but it so materially affected the history of mathematics in Western Europe that I feel obliged to give the leading facts, though I am reluctant to take up so much space with questions of a personal character. The case in favour of the independent invention by Leibniz is stated in Gerhardt's Leibnizissimus Mathematische Schriften in Biot and Lefort's edition of the Commercium Epistocolum, Paris, 1856. The arguments on the other side are given in H. Sloman's Leibnizens Anspruch auf die Erfindung der Differentialrechnung, Leipzig, 1857, of which an English translation with the additions by Dr. Sloman was published at Cambridge in 1860. The history of the invention of the calculus is given in an article of it in the 9th edition of the Encyclopaedia Britannica and in P. Manson's Esquisse de l'histoire du calcul infinitésimal, Gand, 1887. End of footnote. The ideas of the infinitesimal calculus can be expressed either in the notation of fluxions or in that of differentials. The former was used by Newton in 1666 and communicated in manuscript to his friends and pupils from 1669 onwards, but no distinct account of it was printed until 1693. The earliest use of the latter in the notebooks of Leibniz is dated 1675 and was employed in the letters sent to Newton in 1677, and an account of it was printed in the memoir of 1684 described below. There is no question that the differential notation is due to Leibniz, and that the sole question is as to whether the general idea of the calculus was taken from Newton or discovered independently. The case in favour of the independent invention by Leibniz rests on the ground that he published a description of his method some years before Newton printed anything on fluxions, that he always alluded to the discovery as being his own invention, and that for many years this statement was unchallenged. Well, of course, there must be a strong presumption that he acted in good faith. To rebut this case it is necessary to shew that 1. He saw some of Newton's papers on the subject in or before 1675 or at least 1677, and 2. That he thence derived the fundamental ideas of the calculus. The fact that his claim was unchallenged for some years, in my opinion, in the particular circumstances of the case is immaterial. That Leibniz saw some of Newton's manuscripts was always intrinsically probable, but when in 1849 C. J. Gerhardt examined Leibniz's papers he found among them a manuscript copy, the existence of which had been previously unsuspected, in Leibniz's handwriting of extracts from Newton's De Analysi per Equationes Numero Terminorum Infinitas, which was printed in the De Quadratura Curvarum in 1704, together with notes on their expression in the differential notation. The question of the date at which these extracts were made is therefore all important. It is known that a copy of Newton's manuscript had been sent to Tschirnhausen in May 1675, and that in that year he and Leibniz were engaged together in a piece of work. It is not impossible that these extracts were made then. It is also possible that they may have been made in 1676, for Leibniz discussed the question of analysis by infinite series with Collins and Oldenburg in that year, and it is a priori probable that they would have then shewn him the manuscript of Newton on that subject, a copy of which was possessed by one or both of them. On the other hand, it may have been supposed that Leibniz made the extracts from the printed copy in or after 1704. Leibniz shortly before his death admitted in a letter to Conti that in 1676 Collins had shown him some Newtonian papers, but implied that they were of little or no value. Presumably he referred to Newton's letters of June 13th and October 24th, 1676, and to the letter of December 10th, 1672, on the method of tangents, extracts from which accompanied the letter of June 13th. But it was curious that, on the receipt of these letters, Leibniz should have made no further inquiries, unless he was already aware from other sources of the method followed by Newton. Whether Leibniz made no use of the manuscript from which he had copied extracts, or whether he had previously invented the calculus, are questions on which at this distance of time no direct evidence is available. It is however worth noting that the unpublished Portsmouth papers shew that when in 1711 Newton went carefully into the whole dispute, he picked out this manuscript as the one which had probably somehow fallen into the hands of Leibniz. At that time there was no direct evidence that Leibniz had seen this manuscript before it was printed in 1704, and accordingly Newton's conjecture was not published. But Gerhardt's discovery of the copy made by Leibniz tends to confirm the accuracy of Newton's judgment in the matter. It is said by some that to a man of Leibniz's ability the manuscript, especially if supplemented by the letter of December 10, 1672, would supply sufficient hints to give him a clue to the methods of the calculus, though as fluxional notation is not employed in it, anyone who used it would have to invent a notation, but this is denied by others. There was at first no reason to suspect the good faith of Leibniz, and it was not until the appearance in 1704 of an anonymous review of Newton's tract on quadrature, in which it was implied that Newton had borrowed the idea of the fluxional calculus from Leibniz, that any responsible mathematician questioned the statement that Leibniz had invented the calculus independently of Newton. It is universally admitted that there was no justification or authority for the statements made in this review, which was rightly attributed to Leibniz, but the subsequent discussion led to a critical examination of the whole question, and doubt was expressed as to whether Leibniz had not derived the fundamental idea from Newton. The case against Leibniz as it appeared to Newton's friends was summed up in the Commercium Epistolicorum issued in 1712. The evidence there collected may be inconclusive, but at any rate detailed references are given for all facts mentioned. No such summary with facts, dates, and references of the case for Leibniz was issued by his friends, but John Bernoulli attempted to indirectly weaken the evidence by attacking the personal character of Newton. This was in a letter dated June 7, 1713. The charges were false, and when pressed for an explanation of them, Bernoulli most solemnly denied having written the letter. In accepting the denial, Newton added in a private letter to him the following remarks, which are interesting as giving Newton's account of why he was last induced to take any part in the controversy. I have never, said he, grasped at the fame among foreign nations, but I am very desirous to preserve my character for honesty, for which the author of that epistle, as if by the authority of a great judge, has endeavoured to wrest from me. Now that I am old, I have little pleasure in mathematical studies, and I have never tried to propagate my opinions over the world, but I have rather taken care not to involve myself in disputes on account of them. Leibniz's defense or explanation of his silence is given in the following letter, dated April 19, 1716, from him to Conti. Pour répondre de point à point à l'ouvrage publié contre moi, il falloit un autre ouvrage aussi grand pour le moi que celui-là. Il falloit entrer dans un grand détail des quantités de minutes passées il y a 30 et 40 ans, dont je ne me souviens guère. Il me falloit chercher mes vieilles lettres dont plusieurs se sont perdues. Outre que le plus souvent je n'ai point gardé les minutes miennes, et les autres sont salvées dans une grande tasse de papier que je ne peux voir débrouiller qu'avec du temps et de la patience, mais je n'en avoir guère le loisir, étant chargé présentement d'occupations d'une toute autre nature. The death of Leibniz in 1716 only put a temporary stop to the controversy which was bitterly debated for many years later. The question is one of great difficulty. The evidence is conflicting and circumstantial, and everyone must form for themselves the opinion which seems most probable. I think the majority of modern writers would accept the view that probably Leibniz's invention of the calculus was independent of that of Newton, and everyone will hope that they are right. For myself, I cannot however but think it probable that Leibniz read Newton's manuscript De Analysi before 1677 and was materially assisted by it. His unacknowledged possession of a copy of part of one of Newton's manuscripts may be explicable, but the admitted fact that on more than one occasion he deliberately altered or added to important documents
before publishing them seems to me to make his own testimony of little value. In mitigation of his conduct I can only say that it must be recollected that what he is alleged to have received was rather a series of hints than an account of the calculus, and it seems to me that the facts that he did not publish his results of 1677 until 1684, and that the notation and subsequent development of it were all of his own invention, may have led him 30 years later to minimize any assistance which he obtained originally and finally consider that it was immaterial. If we must confine ourselves to one system of notation, then there can be no doubt that that which was invented by Leibniz is better fitted for most of the purposes to which the infinitesimal calculus is applied than that of fluxions, and for some, such as the calculus of variations, it is indeed almost essential. It should be remembered, however, that at the beginning of the 18th century the methods of the infinitesimal calculus had not been systematized, and either notation was equally good. The development of that calculus was the main work of the mathematician of the first half of the 18th century. The differential form was adopted by continental mathematicians. The application of it by Euler, Lagrange, and Laplace to the principles of mechanics laid down in the Principia was the great achievement of the last half of that century, and finally demonstrated the superiority of the differential to the fluxional calculus. The translation of the Principia into the language of modern analysis and the filling in of the details of the Newtonian theory by the aid of that analysis were effected by Laplace. The controversy with Leibniz was regarded in England as an attempt by foreigners to defraud Newton of the credit of his invention, and the question was complicated on both sides by national jealousies. It was therefore natural, though it was unfortunate, that in England the geometrical and fluxional methods as used by Newton were alone studied and employed. For more than a century the English school was thus out of touch with continental mathematicians. The consequence was that, in spite of the brilliant band of scholars formed by Newton, the improvements in the methods of analysis gradually effected on the continent were almost unknown in Britain. It was not until 1820 that the value of analytical methods was fully recognized in England, and that Newton's countrymen again took any large share in the development of mathematics. Leaving now this long controversy, I come to the discussion of the mathematical papers produced by Leibniz, all the more important of which were published in the Acta Eruditorum. They are mainly concerned with the applications of the infinitesimal calculus and with various questions on mechanics. The only papers of first-rate importance which he produced are those on the differential calculus. The earliest of these was one published in the Acta Eruditorum for October 1684, in which he enunciated a general method for finding maxima and minima, and for drawing tangents to curves. One inverse problem, namely to find the curve whose subtangent is constant, was also discussed. The notation is the same as that with which we are familiar, and the differential coefficients of x to the power n and of products and quotients are determined. In 1686 he wrote a paper on the principles of the new calculus. In both of these papers the principle of continuity is explicitly assumed, while his treatment of the subject is based on the use of infinitesimals and not on that of the limiting value of ratios. In answer to some objections which were raised in 1694 by Bernard Nieuwentyt, who asserted that dy by dx stood for an unmeaning quantity like 0/0, Leibniz explained, in the same way as Barrow had previously done, that the value of dy by dx in geometry could be expressed as the ratio of two finite quantities. I think Leibniz's statement of the objects and methods of the infinitesimal calculus as contained in these papers, which are the three most important memoirs on it that he had produced, is somewhat obscure, and his attempt to place the subject on a metaphysical basis did not tend to clearness. but the notation he introduced is superior to that of Newton, and the fact that all the results of modern mathematics are expressed in the language invented by Leibniz has proved to be the best monument of his work. In 1686 and 1692 he wrote papers on osculating curves. These, however, contained some bad blunders, as for example the assertion that an osculating circle will necessarily cut a curve in 4 consecutive points. This error was pointed out by John Bernoulli, but in his article of 1692 Leibniz defended his original assertion and insisted that a circle could never cross a curve if it touched it. In 1692 Leibniz wrote a memoir in which he laid the foundation of the theory of envelopes. This was further developed in another paper in 1694 in which he introduced for the first time the terms coordinates and axes of coordinates. Leibniz also published a good many papers on mechanical subjects, but some of them contain mistakes which shew that he did not understand the principles of the subject. Thus, in 1685 he wrote a memoir to find the pressure exerted by a sphere of weight W placed between two inclined planes of complementary inclinations, placed so that the lines of the greatest slope are perpendicular to the line of the intersection of the planes. He asserted that the pressure on each plane must consist of two components, unum quo decliviter descendere censit, alterum quo planum declive premit. He further said that for metaphysical reasons that the sum of the two pressures must be equal to W. Hence, if R and R prime be the required pressures and alpha and 1/2 prime minus alpha the inclination of the planes, he finds that R minus 1/2 W multiplied by the quantity 1 minus sine alpha plus cos alpha and R prime equals 1/2 W multiplied by 1 minus cos alpha plus sine alpha. The true values are R equals W cos alpha and R prime equals W sine alpha. Nevertheless, some of his papers on mechanics are valuable. Of these the most important were two, in 1689 and 1694, in which he solved the problem of finding an isochronous curve, one in 1697 on the curve of quickest descent. This was the problem sent as a challenge to Newton, and two in 1691 and 1692 in which he stated the intrinsic equation of the curve assumed by a flexible rope suspended from 2 points, i.e. the catenary, but gave no proof. This last problem had been originally proposed by Galileo. In 1689, that is 2 years after the Principia has been published, he wrote on the movements of the planets which he stated were produced by a motion of the ether. Not only were the equations of motion which he obtained wrong, but his deductions from them were not even in accordance with his own axioms. In another memoir in 1706, that is nearly 20 years after the Principia had been written, he admitted that he had made some mistakes in his former paper, but adhered to his previous conclusions, and summed the matter up by saying, "It is certain that gravitation generates a new force at each instant to the centre, but the centrifugal force also generates another away from the centre. The centrifugal force may be considered in two aspects according as the movement is treated as along the tangent to the curve or as along the arc of the circle itself." It seems clear from this paper that he did not really understand the manner in which Newton had reduced the dynamics to an exact science. It is hardly necessary to consider his work on dynamics in further detail. Much of it is vitiated by a constant confusion between momentum and kinetic energy. When the force is passive he uses the first, which he calls his vis mortua, as the measure of force. When the force is active he uses the latter, the double of which he calls the vis viva. The series quoted by Leibniz comprise those of e to the x and log of 1 plus x, sine of x, versine of x, and the arctangent of x. All of these have been previously published, and he rarely, if ever, added any demonstrations. Leibniz, like Newton, recognized the importance of James Gregory's remarks on the necessity of examining whether infinite series are convergent or divergent, and proposed a test to distinguish the series whose terms are alternatively positive and negative. In 1693 he explained the method of expansion by indeterminate coefficients, though his applications were not free from error. To sum the matter up briefly, it seems to me that Leibniz's work exhibits great skill in analysis, but much of it is unfinished, and when he leaves his symbols and attempts to interpret his results he frequently commits blunders. No doubt the demands of politics, philosophy, and literature on his time may have prevented him from elaborating any scientific subject completely, or writing any systematic exposition of his views, though they are no excuse for the mistakes of principle which occur so frequently in his papers. Some of his memoirs contain suggestions of methods which have now become valuable means of analysis, such as the use of determinants and of indeterminate coefficients. But when a writer of manifold interests like Leibniz throws out innumerable suggestions, some of them are likely to turn out valuable, and to enumerate these, which he never worked out, without reckoning the others, which are wrong, gives a false impression of the value of his work. But in spite of this, his title to fame rests on a sure basis, for it was he who brought the differential calculus into general use, and his name is inseparably connected with one of the chief instruments of analysis, just as that of Descartes, another philosopher, is with analytical geometry. Leibniz was only one amongst several continental writers whose papers in the Acta Eruditorum familiarized mathematicians with the use of differential calculus. The most important of these were James and John Bernoulli, both of whom were farm friends and admirers of Leibniz, and to their devoted advocacy his reputation is largely due. Not only did they take a prominent part in nearly every mathematical question they discussed, but nearly all the leading mathematicians on the continent for the first half of the 18th century came directly or indirectly under the influence of one or both of them. The Bernoullis were a family of Dutch origin who were driven from Holland by the Spanish persecutions, and finally settled at Bâle in Switzerland. The first member of the family who attained any marked distinction in mathematics was James. James Bernoulli. Jacob or James Bernoulli was born at Bâle in December 27, 1654. In 1687 he was appointed to a chair of mathematics in the university there and occupied it until his death on August 16, 1705. He was one of the earliest to realize how powerful as an instrument of analysis was the infinitesimal calculus, and he applied it to several problems. But he did not himself invent any new processes. His great influence was uniformly and successfully exerted in favor of the use of differential calculus, and his lessons on it, which were written in the form of 2 essays in 1691 and are published in volume 2 of his works, shew how completely he had even then grasped the principles of the new analysis. These lectures, which contain the earliest use of the term integral, were the first published attempt to construct an integral calculus, for Leibniz had treated each problem by itself, and had not laid down any general rules on the subject. The most important discoveries of James Bernoulli were his solution of the problem to find an isochronous curve. His proof that the construction for the catenary which had been given by Leibniz was correct, and his extension of this to strings of variable density under a central force, his determination of the form had taken by an elastic rod fixed at one end and acted on by a given force in the other, the elastica, also of a flexible rectangular sheet with 2 sides fixed horizontally and filled with a heavy liquid, the lentiaria, and lastly of a sail filled with wind, the velaria. In 1696 he offered a reward for the general solution of isoperimetrical figures, i.e. the determination of a figure of a given species which should include a maximum area, its perimeter being given. His own solution, published in 1701, is correct as far as it goes. In 1698 he published an essay on the differential calculus and its applications to geometry. He here investigated the chief properties of the equiangular spiral, and especially noticed the manner in which the various curves deduced from it reproduced the original curve. Struck by this fact, he begged that, in imitation of Archimedes, an equiangular spiral should be engraved on his tombstone with the inscription Eadem numero mutata resurgo. He also brought out in 1695 an edition of Descartes' Geometrie. In his Ars Conjectandi, published in 1713, he established the fundamental principles of the calculus of probabilities. In the course of the work he defined the numbers known by his name, and explained their use, and he also gave some theorems on finite differences. His higher lectures were mostly on the theory of series. These were published by Nicholas Bernoulli in 1713. John Bernoulli. Johann Bernoulli, the brother of James Bernoulli, was born at Bale on August 7, 1667, and died there on January 1, 1748. He occupied the chair of mathematics at Groningen from 1695 to 1705, and at Bale, where he succeeded his brother from 1705 to 1748. To all who did not acknowledge his merits in a manner commensurate with his own view of their importance, he behaved most unjustly. As an illustration of his character, it may be mentioned that he attempted to substitute for an incorrect solution of his own on isoperimetrical curves another stolen from his brother James, while he expelled his son Daniel from his house for obtaining a prize from the French Academy which he had expected to receive himself. After the deaths of Leibnitz and L'Hopital, he claimed the merit of some of their discoveries. These claims are now known to be false. He was, however, the most successful teacher of his age, and had the faculty of inspiring his pupils with almost as passionate a zeal for mathematics as he felt for himself. The general adoption on the continent of the differential rather than the fluxional notation was largely due to his influence. Leaving out of account his innumerable controversies, the chief discoveries of John Bernoulli were the exponential calculus, the treatment of trigonometry as a branch of analysis, the conditions for a geodesic, the determination of orthogonal trajectories, the solution of the brachistochrone, and the statement that a ray of light traversed such a path that sigma mu ds was a minimum, and the enunciation of the principle of virtual work. I believe that he was the first to denote the accelerating effect of gravity by an algebraical sign g, and he thus arrived at the formula v squared equals 2gh. The same result would have been previously expressed by the proportion v1 squared is to v2 squared as h1 is to h2. The notation phi x to indicate a function of x was introduced by him in 1718 and displaced the notation chi or xi proposed by him in 1698, but the general adoption of symbols like little f, big F, phi, and psi to represent functions seemed to be mainly due to Euler and Lagrange. Several members of the same family but of a younger generation enriched mathematics by their teachings and writings. The most important of these were the three sons of John, namely Nicholas, Daniel, and John the Younger, and the two sons of John the Younger who bore the names of John and James. To make the account complete, I add here their respective dates. Nicholas Bernoulli, the eldest of the three sons of John, was born on January 27, 1695, and was drowned at St. Petersburg, where he was professor, on July 26, 1726. Daniel Bernoulli, the second son of John, was born on February 9, 1700, and died on March 17, 1782. He was professor first at St. Petersburg and afterwards at Bale, and shares with Euler the unique distinction of having gained the prize proposed annually by the French Academy no less than 10 times. I refer to him again a few pages later. John Bernoulli the Younger, a brother of Nicholas and Daniel, was born on May 18, 1710, and died in 1790. He was also a professor at Bale. He left two sons, John and James. Of these, the former, who was born on December 4, 1744, and died on July 10, 1807, was Astronomer Royal and Director of Mathematical Studies at Berlin. while the latter, who was born on October 17, 1759 and died in July 1789, was successively professor at Bale, Verona, and St. Petersburg. End of section 27.